A truly revolutionary event in human history is unfolding before our eyes. No one can deny that AI is transforming our lives and is poised to bring about monumental change to our future. Healthcare in particular is undeniably one of the sectors that will be the most profoundly impacted by AI. Guiding this powerful trend in the right direction is the critical challenge which makes today's symposium exceptionally significant. I believe medical AI delivers two key messages. The first, it champions patient-centered medicine. And second, it facilitates the democratization of healthcare. Physicians must not resist this tide, but rather ride the wave to maintain their essential role as primary healthcare providers. However, we face a crucial task. Our collective responsibility is to strive to prevent the polarization that might arise amidst the rapid change driven by AI. I wish the Korean Foundation of Cancer Research and the Korean Cancer Association, our esteemed co-hosts, continues and infinite success. Furthermore, I extend my deepest gratitude to all the distinguished speakers and panelists presenting here today. Thank you so much.
Next, Yoonok An, the president of the Korean Foundation for Cancer Research, will give us the welcome address. Please.
Good afternoon, ladies and gentlemen. First of all, thank you very much for coming. On behalf of the Korean Foundation for Cancer Research, KFCR, I would like to warmly welcome you to the Seoul International Cancer Symposium, SICS, which is the joint meeting of the KFCR and the National Academy of Medicine of Korea, NAMOK, and the Korean Cancer Association, KCA. The KFCR was founded in 1988 and has had annually the SICS since 1990 as a scientific meeting which contributed to activation of cancer researches in Korea as well as international collaboration. Since 2018, the SICS has been co-hosted with the National Academy of Medicine Korea, NAMOK, and since 2023, 2 years ago, the Korean Cancer Association, KCA, has joined as a co-host. Professor Han, the chairman of the National Academy of Medicine, I appreciate him, and also Professor Sunyoung La, the chairman of the Corporate Relations Committee of the National Academy of Medicine Korea, and also Chief Director of the KCA. I greatly appreciate her for the organization of this symposium. Well, as you can refer to the program of this symposium, the main theme of today's meeting is AI and precision medicine, the new era of the cancer care. Some central issues and topics on the theme will be presented and discussed. And as well, a plenary session on the application of AI and DNA-based digital twins in precision will be open. Today, we are very fortunate to have with us very eminent and leading scholars on the related area of our main theme as speakers. I'd like to express my special appreciation to them for their acceptance of our invitation. I'm so happy to have the honored guest for this meeting. Finally, once again, I'd like to bid a warm-hearted welcome you all to participate in the symposium. And my special thanks go to them who have taken time out of their year-end busy schedule. I wish all of you fully enjoy today's program until the end, and the program a resounding success. Thank you for your kind listening.
Next, Sun Young-ra, the president of the Korean Cancer Association, will give us a congratulatory speech, please.
Good afternoon. It is my pleasure to welcome all of you to the Seoul International Cancer Symposium 2025 with a special thanks to the outstanding speakers. As the chairman of the Korean Cancer Association and the chair of the External Relations Committee of NAMOK, I'm honored to speak on behalf of both organizations together with our co-host, Korean Foundation for Cancer Research. For the last 5 years, our three institutions have collaborated to host this international symposium addressing important and timely topics in the cancer field. This year's theme, AI and precision medicine, is particularly relevant as we explore in the rapid progress of AI and its meaningful applications in oncology. The sessions prepared for today, from AI-driven clinical decision support to on-device AI, clearly demonstrate how innovation is reshaping cancer research and cancer care. These are no longer just ideas, they are becoming real in the medical practice. But still, we confront more opportunities and challenges. As we stand at the intersection of medicine, AI technology, and the data science, collaboration is more important than ever. I believe the partnership among all these organizations reflects the collective effort needed for the future. I deeply appreciate to all speakers and participants for dedication to advancing cancer science. I hope today's discussion will inspire new ideas, strengthen cooperation, and ultimately improve the outcome of cancer patients. Thank you again for joining us, and I hope you enjoy the symposium. Thank you.
Thank you, President. We will now begin session 1, the Clinical Decision Supporting System. It is chaired by Professor Kyung-Hwa Park from Korea University and Professor Lee-Kyu Chi from Seoul National University. Professors, please.
Well, we'll start off with the topic CDSS, which stands for Clinical Decision Support System. As you all know, we have 4 distinguished speakers, and I'll be chairing the first 2 speakers, and Dr. Park by my side will chair the last 2. So first speaker we have today is Professor Seung-Chan Yu. He's a graduate, he's an alumni of Yonsei University, and he went on, after finishing his residency in internal medicine, he had his PhD in biomedical data science at Aju University. After finishing his course, he's joined the faculty and he's now assistant professor at Department of Biomedical Systems Informatics at Yonsei University College of Medicine. The title of his talk will be Integration of Large Language Model into Clinical Practice. Please welcome Professor Yu with a round of applause.
Thank you for a kind introduction, Chair. And it is my great honor to be here and present about the integration of LLM into clinical practice, the YNAP project. This is a story about how we developed and why we developed the LLM for the hospital and how we integrated this into the actual clinical practice and how we use it right now. This is my disclosure. We know that the importance of medical record is increasing, and then there is a growing demand for medical data utilization. But at the same time, we witnessed the mass resignation of the residents from the hospital more than a year, and then at the same time, we also see the growing demands for the medical record and the medical care. So this makes a perfect storm in Korea, the last man and more work. So, there is no doubt that we need generative AI or LLMs in medical knowledge, medical domain, which is capable of both English and Korean. And this project had three pillars. First of all, we had to create a data and constructed the data set for the AI development. And second, we had to develop them dedicated medical LLMs in this field, and then we had to develop the actual clinical service for the use. And there are numerous expected benefits in this project. Of course, we expected that this project can reduce the burden of clinicians, but I think that the more important thing is that standardization medical records and ensure the continuity of care. Even though in the hospital, usually the single doctor wrote every medical record for a single patient, but the records are read by multiple people in the hospital, including many doctors, professors, fellows, junior doctors, or senior residents, as well as multiple nurses in the wards, and then many other health caregivers. So, to improve patient trust and safety, it is really essential to standardize the medical records, and which is really challenging currently. So we started the project named Why Not, which is a very bold named project. By using this name, I'd like to imply the innovation. Why not? Why can't we? And then this stands for that you are knowledgeable navigator of treatment. But by using this name, I'd like to imply sovereignty, efficiency, integration, scrutiny, as well as collaborations. So this is, very, once again, the very bold project. We started this project from July last year, and that, we noticed that the strike or resignation of residents will continue more than a year after June last year. So that's why we started from July last year. And then we spent only 4 months from the beginning of this project and to complete this project, finally using it. This is actually the very massive collaborative project integrating, including many stakeholders in the hospital and outside of the hospitals. So in the hospital, the physicians are really dedicated themselves to this project, but also other staffs in many diverse departments also worked hard for this single project. And there are 3 different industries dedicated to several factors such as project management, EHR integration, and the development of LLM. There are 3 3 works. First, we had to develop medical LLMs, and then second, we developed the clinical practice, clinical service, and then we developed how to thought about how to integrate this system into actual EHR and then actual clinical workflow. So for designing the clinical service, we had iterative consulting session with clinicians and the teams of medical records in the hospital. We specify the goals first, and then configure the input data, and then after pilot application, we review the draft and the revision. And after all of this, we started the specification of a goal once again, on and on. So this is a very iterative session to balance between the expectation of clinicians and the capability of about what technology actually can do. We choose 5 use cases for the pilot project. The first one is discharge note for emergency medicine. Second, pre-operative evaluation note for anesthesiology, and admission, progression, and discharge note for general hospital. To configure the input data to be ingested in the LLM, we screened more than 2,000 different formats of medical records in the hospital. And we selected about 1,000 of medical records, which will be valuable for medical LLM. And then we mapped these 1,000 of medical records into FHIR, HS FHIR, which is a standard format for global use. And then, meanwhile, we had to develop the bilingual medical large language model. We used 90 gigabytes of medical corpus and 90 gigabytes of general corpus to develop this one. Please note that at the time, like last year, July, there was no DeepSeek. So, there was no available bilingual LLM, as well as, LLM specified medical knowledge. That is the reason why we had to develop our own LLM at the time. We developed this based on the 2 different phases. Because this is the first project developing LLM and actual use of LLM in the hospital, we had to thoroughly, evaluate the effectiveness and safety of this system. What would happen if we use it in the actual hospital. So we conducted 3 different kinds of the evaluation. First, pre-deployment evaluation. Second, in silico validation. And third, post-development deployment surveillance. The first one would be similar to the phase 1 or 2 clinical trials, while the second one is kind of an analogy to the phase 3 clinical trial. And the third one, the post-development surveillance, would be similar to the phase 4 trial or the post-marketing surveillance. So before actual integration of this system into EHR, we quickly evaluate the safety and effectiveness of this AI system. So 2 evaluators read the 100 cases, 100 records, and the scores from them actually was quite good. So we proceeded this to integrate it within the EHR. And then just like the phase 3 clinical trial, we conducted kind of the crossover study. So by using the 6 residents, we made them wrote 50 notes respectively, and then after the first session, we made them write the identical notes based on the AI generated drafts. And then all of these notes were evaluated by the independent 3 clinicians. This is the UI we used for the evaluation by the evaluators. And the results were astonishing. These black bars mean the scores of the human-only notes. And then these light blue bars indicate the results from the AI-only notes. And the third, the dark blue bars means the result from the human notes based on the AI notes. And then across the four scores, completeness, correctness, conciseness, and clinical utility, you can see that usually the human records were worse than AI notes or the AI-assisted notes. And then generally, the AI-assisted notes has the better clinical utility compared with the human-only notes. And then we also found that this can reduce the documentation time by over 50%. So this shows how it works. At that time, we made the clinicians to prescribe, AI use in the prescription screen. After that, they have to move their click mouse into to write the actual discharge notes. When they click the notes, you can see that automatically generated discharge notes in the pop-up message, and then these describe the past history of these patients and what happens in the emergency department room, and that the final plans. Now you know that all of these informations are actually available in the EHR. So by using the information in the EHR, we can generate this kind of the notes without human inputs or human knowledge. So if you are satisfied with this, and then you can just transfer this note into the actual enter notes. Usually, the doctors revise 1 or 2 sentences. So this services has been implemented from last year, November. So we have used this system for a year. This shows how AI generate the notes for the pre-operative evaluation. So usually the most surgeries are, scheduled. So when you click the note for the scheduled surgery, and once again, there is a pop-up note describe the very comprehensive patient history. Usually the junior residents in the anesthesiology department has to spend their time to summarize the patient history for the scheduled surgery. Now, there is no one to do this in the hospital. So now in our hospital, AI do the summarize this kind of the very comprehensive patient records. Before implementation of why not, many medical records actually lack the very essential items such as past history or the regional visits. And then the expression was very inconsistent across the users and across the records. Sometimes they use the plus or minus to show the present or absent. So, but after implementation, the records are heavily standardized. So after implementation of this system, all records has automatically very essential items. And then it makes many house staffs in the hospital read it easy and understand the history of the patients very easily. This study was published in JAMA Network Open in this month, so I'm so happy about this. And actually, the Dr. Jeans from the NYU Langone Health was a reviewer of this study, and then he kindly wrote the commentary for this study. He wrote that while most studies evaluating generated AI for discharge summaries have used consumer-grade model, which is ChatGPT, but our study focused on a lightweight, bilingual, open-source model tuned to clinical Korean and English notes. We show that the on-premise deployment designed to address the data security and regulatory limitations enhanced the model's feasibility in clinical environment where patient privacy is paramount. And our study represents one of the most thoughtful and methodological rigorous evaluation to date of an LLM assistant for clinical documentation. And we show that even a relatively small locally hosted model, if fine to the institutional needs and evaluated with care, can yield substantial improvement in notes quality and workflow efficiency. And this is another study we are doing for post-deployment surveillance. So we conducted 3 consecutive surveys right before implementation and right after implementation. And we conducted a third survey a month later. This shows the changes in workload perceived by physicians. So you can see that overall workload gradually decreased after implementation. But what is more interesting to me is the changes in concerns about the LLM-based writing. Unexpectedly, there was substantial concerns from physicians about the LLM implementation, including false information and loss of control as a doctor. But after implementation, these kind of concerns decreased abruptly, and then it continues to a month later. And then this is a perceived writing time that they responded that this system decreased the writing time about 2/3. Actually, compared with the last year, after implementation, we found that the completion rate of the note was increased by 5% point. And we are currently developing this system further to broad the applications such as checkups for checkup and for outpatient medical records. And then in the next year, we're gonna initiate the general chatbot for EHR, and we are gonna make this as a platform linking EMR and diverse AI services. This is a very relevant, I think this is a very relevant service for oncology, because many patients for oncology were transferred by a hospital, and they gave us tons of papers from the hospital. And then this system will automatically summarize the medical records of the external hospital, as well as visualize longitudinal patient trajectories over time. So this project, by using this project, we built the world's first on-premise LLM-based automated clinical document draft generation systems. And by integrating with EHR, it reduces clinical documentation burden on medical staffs. And this operates in on-premise environments to ensure the sovereignty, and it also provides a multilingual support. So by using lightweight model like this, we can minimize the latency and optimize the cost efficiency, which is very crucial in a Korean system. Thank you for your attention. Thanks.
So now the floor is open for a question, if there be anyone. And we do have very limited time, so just quick question I might have. So would there be any priorities against adopting this system? Because you mentioned that there, first 5 use cases were selected on certain criteria, and you plan to expand it to other services. So would there be any service that that would be less likely to benefit, or will be far behind all other services?
Yeah, actually, there are numerous challenges in the system, even though I just showed the only bright side. But just one thing I noted that, actually, the senior doctors prefer this more than junior doctors. Usually junior staff have their own very stubborn. I think they are more stubborn than senior doctors, and senior doctors prefer this because they do not need to navigate the EHR. Because before mass resignation, they never written the notes for the in-hospital patients. So during this mass resignation, they had to navigate the EHR, which was very unfamiliar to them, and so it makes they were really enjoyed this service, while the more junior faculty did not like it compared with the senior doctors. So, but there are numerous challenges.
Thank you. So because of the duration of time, well, thank you, Dr. Liu, and please give a round of applause to you, and we'll went on to our second speaker. Thank you. The next speaker we have is Professor Sang-Jun Park. He's also an alumni of Yonsei University, and he had his graduate course at Korea Advanced Institute of Science and Technology. After finishing his fellowship, he has joined the faculty, and he's currently clinical assistant professor at Department of Radiation Oncology, Yonsei University College of Medicine. The title of his talk will be Decision-Making and Planning Support for Radiation Therapy Using State-of-the-Art AI Models. Please welcome Professor Park.
Thank you for a kind introduction. It's truly a pleasure and a great honor to speak here in the Global Cancer Symposium here. So my name is Sang-Jun Park, and I'm assistant professor, clinical assistant professor in the radiation oncology department in Yonsei Cancer Center. And today I would like to share some my thought about how state-of-the-art AI model, like a generative model, can be applied for decision making, and also planning support for radiotherapy planning, and also the follow-up. So here is a quick overview of today's talk. And actually, when I start my PhD course in KAIST, the mainstream of the AI algorithm is, the famous convolutional neural network, namely CNN. However, it changed a lot with the invention of the transformer and also vision transformer, and nowadays large language model. So now with the growing popularity of LLM, this time can be considered as the time of the transformer, which is backbone of the large language model. So you may be familiar with these names, OpenAI on Google, Anthropic, Meta, and Grok, and maybe these names like Alibaba or DeepSeek, which is a Chinese company. So as you can see in the figure, the global AI investment, not by government and by other companies, are led mainly by the USA and China, and actually exploded recent years, reaching over $600 billion worldwide. So maybe the recently popular AI model can be considered as kind of generative AI model, and this generative AI model can be categorized as a subset of the deep learning. And actually, a conventional deep learning model can be divided into two categories, like a discriminative AI model and also generative AI model. And discriminative AI model can be considered as an AI model developed for classify or predict the specific the decision boundary. And generative AI model can be considered as some model that can actually generate data point like a text or image or video. So for example, if the model classifies dog image as the dog or just a cat, it can be considered as kind of a discriminative AI model. And if the model generates dog image similar to the input image, it can consider as kind of generative AI model. So let's get back to the concept. And the popular large language model and image generation model like diffusion model all belongs to the category of the generative AI model. So they made a boom recently with their powerful flexity to perform the simple chatbot, perform as a simple chatbot like a ChatGPT or Gemini, or maybe you are already familiar with these images like a Ghibli style image generation from the text prompt, and recently updated the real-like video and audio generation with Sora, Veo, and other models. So maybe this popularity of LLM is actually from their flexity to handle the different length data because it was made with the transformer, which is trained with the generative pre-training. So as you know, named GPT is from the generative pre-trained transformer. So this kind of transformer is actually underwent generative pre-training, which is trained to predict simply the next word with a large corpus of the text. And by training this model for the downstream task like common sense reasoning and translation and so on, the model can get the flexibility to perform for unseen tasks like the medical QA or something. So an interesting thing happened here is that the generative pre-trained model in large scale, the phenomenon called emergence, which stands for a new ability not present during training, rises like this blue graph. As you can see in the figure, large parameter-sized model trained with sufficient data can acquire ability for unseen tasks. Means the model can get the flexibility and ability for the new downstream task, which is the reason for the nowadays popularity of the large language model. So with this outstanding flexibility, instead of building one model for specific tasks like diagnosis and also for segmentation and prediction for survival or something, we can now use a single foundation model and adapt it for multiple tasks like text generation, language translation, QA, and so on. So this is a huge shift because it makes AI much more accessible to researchers or clinicians like me. So next topic is how this kind of large language model can actually change the clinical practice and also decision support in the specific field of radiation oncology. So maybe you're not familiar with radiotherapy workflow. We undergo actually this 5 workflow from the diagnosis and consultation in the outpatient clinic to CT simulation and treatment planning and dose calculation and treatment delivery and follow for the all radiotherapy patient. And maybe the large language model and other generative AI model can assist every process of this workflow for radiation oncology. So the first application will be for the diagnosis and consultation. So, for example, my research group performed a project called RT-Serve to predict those who will have poor prognosis after radiotherapy because not little number of patients die after radiation therapy. For about 10 or 20% of patients die within 30 days after the radiation. So actually, for this kind of subset of patients, radiotherapy will not be beneficial. So traditionally, this kind of patient were classified with structural data like a vital sign lab or other structured data like albumin or hemoglobin or something. But as you know, not only this structural data help to predict the patient, because when we see the patient, what we think importantly is the general condition of the patient and the trend of the disease control and so on. But that kind of information is not actually structured from the EMR data. So I used a large language model like Llama 70 billion model to structuralize this unstructured data from the text-based EMR. So when use this kind of text-based EMR structured data, as you can see in the bar graph, the performance of the prediction improves significantly after the structuralization. And one more interesting is that the general purpose large language model like ChatGPT or Llama significantly outperform the medical domain fine-tuned model like MedLlama or something. As you can see in the table, the medical fine-tuned model work very poor, showing that their language ability decreased after the adaptation for the language adaptation for the specific medical domain. And secondly, this kind of large language model can be used to actually target control for the radiotherapy target, like a radiation oncologist, with the multimodal possibility of a large language model. So in my research with Ms. Dr. O in MGH, we developed a multimodal AI model for radiotherapy, target controlling based on the large language model, reflecting the common practice pattern of the human radiation oncologists who see not only the CT image but also the EMR to precisely control the target volume. And as you can see in the figure, the large language model-based multimodal model significantly outperformed the vision-only, the CT image-only model, not only for simple breast case, but also for the regional low irradiation case. And this kind of thing actually proved for the entire data set with quantitative analysis showing the performance improvement, especially for the external validation. And the difference between this external validation 1 is the external validation 2 is that external validation 2 is more different setting, compared with the training data, meaning that different vendor and different acquiring setting for CT simulation was used for external validation 2, showing that this kind of multimodal model show powerful generalization performance in different settings. So we expanded this framework to the whole workflow of the radiation oncology, some kind of agentic workflow, which is now popular for the large language model application. From the note summarization from the MRI, ultrasound, and pathology report, and after then the plan suggestion from this note, and the target controlling from the previous study. So this kind of holistic workflow can be considered as application of large language model as an agent for the radiotherapy planning and decision support. And after target controlling and planning, one important thing is the dose calculation. Even though this is not my study, Nature paper published in 2025 showed that AI can improve by its own feedback, like a backpropagation for the AI model, which is very common for training AI model for AI model from the loss of the calculation. So this kind of text grad resemble backpropagation by revising each prompt from the loss of the calculation. So they applied it for the dose calculation for prostate cancer. And as you can see, the initial dose distribution is not good, showing the excessive dose to OAR and a poor coverage of the target volume. But after iteratively revise each prompt again and again, the control, the target coverage become more concise, and also the OAR dose decrease after the iteration, showing that this kind of large language model-based automation can be applied for the dose calculation process of the radiation oncology. And the final thing, as a medical doctor, should do after the radiotherapy is a follow-up. So I applied the generative AI model like a diffusion model, state-of-the-art generative AI model for image for the objective cosmesis evaluation for the breast cancer patient. In 2019, the model like GAN, generative adversarial network, were used to identify anomaly by reconstruct abnormal image to normal image and calculate the anomaly score by subtracting these two images, anomal image and reconstructed normal image. I use this concept to the breast cancer patient by using the state-of-the-art diffusion model to reconstruct this anomal data to under the normal data. And by subtracting this normal data from the anomal data, I can identify where is the anomal lesion and quantify the anomaly score like that. So as you can see in the graph, the excellent patient show a relatively low anomaly score, and the poor patient showed a relatively high anomaly score, showing that this kind of quantification is possible without any label, just applying the anomaly detection technique for the objective cosmesis evaluation with generative AI model like diffusion model. But I think this kind of large language model and other generative model is not perfect. So you may be already familiar with this kind of Gartner's hype cycle. And every new technology goes through the phase of inflated expectation before reaching the plateau of productivity. So maybe we are now here or something, but the question is that we have to consider whether where are we now, and I think this kind of technique like large language model and generative model should be treated with caution. So actually, a large language model and other generative model is not perfect. As you know, they hallucinate. And their hallucination is a fundamental problem because the training data for large language model is just a subset of the real-world data. So many says that the fundamental limitation of the hallucination cannot be perfectly overcome. And also, even though the context window of the recent large language model expand, but actually, when you give the long context, the precise context cannot be reconstructed with a large context window. So many techniques like retrieval augmented generation, chain offset, and self-consistency and sampling were introduced to overcome this kind of problem, but not perfect now. So this kind of generative model should be treated with caution, but I think the state-of-the-art generative model can change clinical practice and decision-making with its potential in the radiation oncology. So some people say that the impact of the AI model will be as big as a smartphone revolution, and others say that it will be as big as the internet itself. And even someone goes further, saying that it's kind of discovery of a fire. We don't know exactly how big the change will be with the generative AI, but one thing is certain that it will bring major transformation, not only in the field of radiation oncology, but also for all the application of the cancer patient, but not only cancer patient, medical domain. So I'm truly excited to see this kind of change happen. So finally, I would like to thank my collaborator who made it possible for me to do this kind of beautiful project. And thank you for attention.
So again, the floor is open for questions, if there be any. We might have time for one or two questions. If not, I'll just try to ask. So in your prospect, what would be required or recommended for new radiation oncologists to get trained to be ready for the time to come?
You mean, thank you for a good question. You mean this era of generative AI? It's very important question, yeah, because medical education and also resident training is largely affected by introduction of the large language model and that kind of thing. So, in my opinion, before getting accustomed to some level, the use of large language model should be cautiously applied because it may disturb them from skilling. So maybe some very cautious approach should be done for, especially for the earlier career resident, in my opinion. Thank you.
Thank you. So, oh, okay, we have a question from floor.
Hello, I'm an undergraduate and I'm not really used to AI models, but I have a question regarding are there any security risks? Because if you use LLMs, you're actually connecting to a different server outside, I think. So I'm curious if those hospital datas, if there's any way you can stop that.
That's a good question. Thank you for your question. And that's possible. So I use not ChatGPT, the local large language model like Llama, to do this kind of study in our hospital setting. So in my opinion, using data with ChatGPT or other proprietary LLM is not proper because it's data from patient. So if you want to do research with this kind of large language model, I recommend you to use the open source large language model in our hospital setting to prevent data spillage, data leakage problem, privacy protection of the patient.
Can I ask one question? Thank you so much for the great work. Also, I'm naive to this type of the thing, and I'm always curious about the hallucination. And you mentioned that is it the LLM is always making that hallucination as a fundamental problem, or is it a developer's idea or something? So I was curious, LLM cannot overcome that hallucination ever, because you always, everybody says cautious. How cautious? We don't know how cautious to use it. So that is my question.
Thank you for a very good question, and it's a very fundamental question asked by many researchers. And there is many review articles that investigating whether hallucination can theoretically overcome or not overcome perfectly. But as you know, recent LLM like Gemini or other Gemini 3 or other model hallucinate less compared to 2 years ago model. Yeah, but still there is hallucination, and there is no guideline to detect hallucinations. So technique like self-consistency using LLM to ask again and compare the answer, and that kind of technique, or retrieval augmented generation to ground information from some credible source is used. But maybe it improved a lot, but not perfect now. So actually, I'm not sure whether this kind of hallucination is perfectly overcome. But human also hallucinate. We also say inaccurate thing. So maybe someday the LLM will reach the level of the human, even though there is some hallucination, but it will not make a large difference compared with human expert. Yeah.
Okay, last one. Well, please make it quick.
Yeah, I didn't know that I have to speak in English. Yeah, I have no prior information, yes, before I came here. So I was wondering if you have any special or strategic way to prevent or minimize the adverse effect of the hallucination. And also, I hope you to address and responsibility in case of the erroneous and that it's a not clear decision or diagnosis. So to 2 points, I'd like to hear your opinion.
So thank you for a good question. For the first question, maybe many techniques are used for to overcome hallucination. Giving specific guideline or specific context before asking LLM to answer will reduce hallucination, and also explicitly saying that do not hallucinate also work for some extent, but not perfect. So that kind of approach can be used to make hallucination less. But the fundamental way to reduce hallucination using good LLM. Yeah. Recent LLM with great performance, hallucination less significantly compared with other less performing open source model also. So, and for second question, what was your second question?
So in case of some erroneous by human fault, as erroneous decision making or the diagnosis can be generated. So in that case, I hope you to address about the responsibility of the research.
Actually, nowadays the responsibility should be charged for a medical doctor. Yeah, they have their meant that LLM can hallucinate in their background. So human doctors are in charge of the kind of erroneous result. If there is some error in radiology report or something, maybe it will not change soon. Yeah, in my opinion. Yeah.
It will take time to reach
take time to
consensus,
change.
right?
Yeah. So maybe big tech do not want to take charge of the kind of erroneous situation.
Okay, thank you very much, Professor Park.
Thank you.
Okay, next, we are moving to the next speaker, Professor Seung-eun Song, the professor of Korea University Annam Hospital in the Department of Radiology. So Professor Song graduated from Korea University and received a PhD from the same graduate school of Korea University, and then she was trained and then served as the clinical assistant professor at the Seoul National University Hospital, and now she joined to Korea University Annam Hospital from 2016 to now. So today the topic is the integration of AI in radiologic decision making. Please welcome with big applause.
Thank you, Chairperson, for nice introduction. Good afternoon, everyone. I'm very pleased to be here and to present my topic regarding integration of AI in radiologic decision making. The application of medical AI in radiology is rapidly advancing, transforming how imaging data is interpreted and utilized in clinical practice. The main areas of AI application in radiology include image interpretation, report generation, image quality enhancement, workflow optimization, and predictive analytics. And all of these contribute to clinical decision support. The most remarkable achievement in the medical AI field is in the area of image interpretation. Image interpretation consists of detection, classification, measurement, and segmentation. In this lecture, I will discuss the most important aspects of AI in radiology, detection, and classification in order of musculoskeletal, neuro, chest, and breast. In the musculoskeletal domain, AI has made significant progress in fracture detection, bone age assessment, skeletal measurement, and osteoarthritis grading. This is the list of FDA-approved MSK AI software. Among them, OsteoDetect is the first FDA-approved AI software in radiology. These are Korean products approved by Ministry of Food and Drug Safety in Korea. Let's take a look at some representative companies that have commercialized fracture solutions. I think BoneView is one of the most clinically proven solutions. Buccal fracture of the first metatarsal bone, which is not easy to detect, but it is detected by BoneView. This is another product, Azmed from France. The solution is able to detect all types of fractures, dislocations, and joint effusions for all age groups, including pediatric, on the plain radiograph. Recently, the solution updated with the datations capability that estimates whether a fracture is recent or old. I think it's a timely development. A meta-analysis of 7 commercial products revealed that most of all AI solutions showed excellent diagnostic performance and reported that the highest performance when reading with AI reference. However, it wasn't good for the ribs and spine. Recently, the United Kingdom's National Institute for Health and Care Excellence has endorsed AI technologies for fracture detection, recognizing their ability to improve diagnostic performance in urgent care compared to standard care alone. AI has been promising in accurately detecting fractures on imaging, enhancing triage, diagnosis, and patient care, particularly in emergency settings. So I think AI is reshaping emergency care, and I hope that happens in Korea. Let's move on to the bone age assessment. I think bone age is one of the fields where AI has been deployed into clinical practice the fastest. And I know bone age assessment by Buno is the first AI software in Korea. Whereas Bone Expert is a pioneer and the most popular in Europe. There are a bunch of bone age AI solutions. On the left is an international company's bone age. AI, and on the right is a domestic bone age AI. In our hospital, we use AI solutions for bone age assessment. Currently, all processes are done with zero-click. Just like in the field of fractures, AI bone age assessment has been well validated with comparative studies on the commercialized products. Accuracy is quite high, and it is clear that the technology has reduced the burden on radiologists. Let's move on to the skeletal measurement. This patient is a candidate for total knee replacement arthroplasty named as TKRA. We know that the measurements are crucial for evaluating geometry in TKRA surgery. However, to be honest, we are so busy and not comfortable with this complex measurement. IB Lab is a leading Austrian company with solutions for long leg, hip, and spine and foot measurement. AI is going to reshape our practice of orthopedic measurement soon with the generalizability test passed. A future will soon come where measurement values are inserted into the table format in radiology reports, hybrid reports, or DICOM's secondary capture, allowing radiologists to simply find and interpret the red flags. Let's move on to the next topic, knee OA. Commercial AI software focus on Kallgren-Lorenz grading, diagnosing early OA, and prediction of OA progression. A lot of studies for KL grading automation conducted. This is a comparison of AI models. The performance is similar to non-expert. Let me show the UI of various KL solutions. UI are most the same. All right, let's go ahead and move on to the neuropart AI. In neuropart, detection and classification include hemorrhage, small vessel disease, acute cerebral infarction, and cerebral aneurysm. This is the list of FDA-approved neuro AI software. To date, none of the FDA-approved neuro AI software solutions have been developed by Korean companies. Also, there are no specific MFDA's approvals for neuroimaging AI. However, many companies in Korea are currently developing such solutions. This AI is an FDA-cleared medical AI company that provides stroke workflow solutions, large vessel occlusion, brain hemorrhage, and CT perfusion analysis. This case shows that the accurate detection of small subdural hemorrhage in the left frontal convexity using SK Corporation's AI system with a hemorrhage confidence score of 98%. This case demonstrates the accurate detection of a small subarachnoid hemorrhage in the left parietal sulcus using SK Corporation's AI system with a hemorrhage confidence score of 80%. This case represents a false negative as the AI failed to detect a considerable amount of left subacute hemorrhage. This case is the representative case using JLK for brain infarction detection. It accurately detected a small infarction in the right lentiform nucleus with a confidence score of 99. This case is the representative case using JLK brain aneurysm. The company reported that the sensitivity was 95%. Now, let us move on to the chest part AI. The role of AI in chest radiology can be summarized by its key applications in detecting various conditions such as lung nodules, pneumonia, pleural effusion, and pneumothorax detection, tuberculosis screening, and chronic lung disease monitoring. These are summarized FDA-approved chest AI solutions. And these are summarized MFDS-approved chest AI solutions. You can see Buno and Lunit here. When using the Korea-developed Lunit AI chest, the AI group showed a significantly higher AUC than non-AI group for detecting actionable lung nodules and malignant lung nodules. Another major advantage of AI is that it does not increase the number of false positive cases, and using AI substantially improves radiologist sensitivity for detecting lung cancer. Now, let us move on to the final topic, breast imaging. In breast AI, there are various applications, but cancer detection and characterization are still the most widely used. These are FDA-approved breast AI solutions, and Lunit also received FDA approval. These are summarized MFDS-approved breast AI solutions. In breast section, we already use conventional CAD for mammography, which received US FDA approval in 1990. Initially, these systems relied on handcrafted feature extraction techniques by incorporating machine learning methods. The main advantage is an increased cancer detection rate. However, one significant drawback is poor specificity. In 2020, AI CAD received US FDA approval. AI not only increased the cancer detection rate, but also reduced the number of false positives. This is a case of invasive lobar cancer. Did you find the reason? Here it is, in the left upper outer quadrant. Both conventional CAD and AI CAD detected the region accurately, and there were no false positive regions by conventional CAD. This is another case. Can you find the cancer? Yes, here is the speculated mass in the left upper inner quadrant. Conventional CAD failed to detect the speculated mass, but AI correctly identified it. Lunit Insight was developed using 170,000 images, and they reported that AUC was excellent when using AI alone compared to radiologists with AI or radiologists alone. Then we must ask whether AI is perfect and what kinds of cancer it might miss. Therefore, I conducted a study on cancers missed by AI and published the results in Radiology. Among 1,097 invasive cancers, 14% of cancers were missed by AI CAD. And the first negative result was higher in luminary subtype than other subtypes such as triple negative or HER2 positive. The first negative rate was 14% for invasive cancers and 25% for ductal carcinoma in situ, equally stage 0. Among the 154 missed cancers by AI CAD, 61% were detected by 2 of 3 radiologists. And reason for miss were dense breast, architectural distortion, or masses located outside the mammary zone of the breast. From now on, I will show you several representative cases that AI tend to miss. In the left mammogram, radiologists can detect 2 focal asymmetries here. However, AI failed to detect. And the cancer is revealed as 1.5 centimeters invasive ductal carcinoma, and reason for miss can be explained by obscured by dense breasts. This is another first negative case. We can detect architectural distortion in right upper outer quadrant. However, AI failed to detect. 1.2 centimeter invasive ductal carcinoma was found, and reason for miss was cancer manifested as architectural distortion. This is another first negative case. We can detect a nodule located in the retromammary area. However, AI failed to detect. 1.1 centimeter invasive ductal carcinoma was found by ultrasound. Reason for miss was cancer located in retromammary fat layer. This is the final case. Radiologists can find right nipple retraction with periareolar skin thickening compared to left nipple. However, AI failed to detect. And the cancer is revealed as 2.2 centimeter invasive ductal carcinoma, and reason for miss was cancer located in subareolar area. An AI algorithm can overcome benign findings, potentially leading to an increase in recall rate, named false positive interpretation. And the algorithm can also undercall or miss findings, leading to a missed or delayed cancer diagnosis, named false negative interpretation. Embracing AI more actively while continuously improving our interpretation skills will ultimately enhance patient care. And radiologists who use AI will replace those who don't. In summary, AI in radiology offers higher accuracy and efficiency, but also brings risks like bias and over-reliance. So the fields should move towards supervised human-AI collaboration with well-validated systems integrated into our routine clinical practice. Thank you for your time.
Thank you very much for your excellent presentation, Professor Song. So this talk is open for the questions or comments from the floors. Also, we are accepting the questions from online, so you can leave the messages on the YouTube platform.
Just like GPT, like the quality of data affects how the AI model performs. I'm curious if the medical data quality also affects models like the one that you introduced for breast cancer.
It's a great question, thank you. I think that data quality is very important for AI quality and assessment. So I think that the AI developed in one institution, the result is varied on the according to the institution or company or many techniques. So it is very important to unify the data quality among all institutions or all companies. So it is very important. So, but in our country, in Korea, we use very advanced technique for the brain radiograph, CT or MRI. So it is very good candidate for AI development because Korea has the many advancing techniques in all of the university hospitals or tertiary institutions. So it is the reason why many companies want to work with Korean hospitals. So I think that we have very strong strengths about the data quality.
Okay, thank you. So one more short question. So did you see any difference in detecting cancers between the dense breast versus fatty breast?
Yes, it's a very great question. Because in the background of a fatty breast, AI can detect the cancer very accurately. However, it can miss the cancer obscured by dense breast. So it is the reason why the AI technology in breast imaging should be improved by more feedback.
I see. And also, I think it should be more explored in Asian patients like ours.
Yes, right. In Asian country, over 60% of Asian people had dense breast. So the AI is not working in the Asian women compared to the Western women because the higher rate of dense breasts.
Thank you very much. So because of the time limitation, I'd like to close this session. So I'd like to appreciate for all the speakers for their wonderful presentations. Sorry. So I'd like to introduce the last speaker of the session, Professor Min-Sung Cho from Amazon Web Service. So, so Dr. Cho graduated from KAIST and also graduated from Yonsei University. And then his research interest is agentic AI, cloud computing, data lake, storage, and PACS EMR. So currently, he works for the AWS Korea public sector. So please.
Thank you. Good afternoon. It's an honor to speaking here today. My name is Min Sung Chu. I'm take care of a healthcare team in Korea. So I'm just working in the Amazon Web Services. Okay. Today I'd like to discuss about agentic AI, which is gaining the significant attention in the medical field. I will also briefly demonstrate how agentic AI can be used to develop patient treatment plan. AI agent has been taken world by storm. At AWS, we believe the billion of agents will soon working alongside the humans across the consumer, enterprise, and the industrial settings. They will orchestrate a sophisticated multi-step process requiring context understanding, decision-making, and action-taking. AI agents will fundamentally change how we work and live. Unlike foundation model, AI agents are autonomous software systems that reason, plan, and act to accomplish goals, like compiling research, paying bills, or managing enterprise applications. Agents interact with their environment through APIs, tools, and data stores, decompose high-level objectives into executive steps, and continuously learn and improve over time. AI agency has evolved from the rule-based automation through AI assistant to goal-driven agent operating toward higher-level objectives. The future point toward a fully autonomous system that independently set and execute goals. However, we are still at the nascent stage. Reaching higher agency requires not just better technology, but also governance, trust, and organizational readiness to truly transform. Agentic AI is the next era of AI, but it doesn't replace the generative AI. They coexist. Gen AI excels at content creation and summarization. Agentic AI go further by solving complex problems and taking intelligence action across systems. While Gen AI sparked excitement, many struggle with the business transformation. Agentic AI bridges these gaps, deliver outcomes through intelligent action, not just responses. In fact, Gartner predicts that over a third of enterprise applications will be powered by generative AI and agentic AI by 2028. And at least 50% of the work decision will be made by autonomously by agentic AI by 2028, as compared to 0% in 2024. Also, by 2028, one-third of the interaction with the generative AI services will invoke action model and autonomous agent for task completion. But going from POC to production is very hard. AWS empowers organizations to reimagine business with agentic AI, turning ideas into agent and complexity into autonomy. By reading in agent development, AWS enables secure, reliable agent at scale. The vision is rapidly innovation for all, built on strong foundation of the security, reliability, and operational excellence. What makes agent powerful is their ability to think interactively, to evaluate result, adjust their approach, and continue working toward a goal. They don't just answer questions, but they solve problems through a process of explanation and refinement. We expect a proliferation of the agent addressing different use cases and tasks across the value chain. Let me introduce Amazon Bedrock. Amazon Bedrock is a fully managed service for AWS that provides a single API to across and build application with the leading foundation models from various providers. Amazon Bedrock is cloud platform for the building AI agent and generative applications using open source framework. It provides core agent capabilities like runtime, gateway, memory, identity, and browser tools, plus model function for customizations. And then we also provided enhanced intelligence also. Amazon Bedrock lets enterprise top AI models, including languages, reasoning, image, and video tools. Companies like OpenAI, Meta, Anthropic, with a unique strengths. The following is the introduction of an agentic AI service for life science research, recently released as open source by AWS. Healthcare and life science customers select agent for needs like real-world data, clinical trials, biomarkers, and drug discovery. Industry-specific terminology and ontologies are essential, as they enable intelligent agents to understand, organize, and relate knowledges within each domain. AWS recently released the open source toolkit for life sciences, inspired by the working with a customer like Genetic and AstraZeneca. The toolkit offers a catalog of more than 20 starter agents for proof of concept and multi-agent orchestrations across the life science value chain, including R&D and clinical development. Built on AWS Bedrock, it features a developer-friendly UI and customizable and scalable framework that supports rapid testing and development of agent workflows, all ready for use and further tailoring within your AWS account. If you have AWS or if you have any cloud solutions on your organizations. This image shows us 3 types of AI agent for the life science: biomarker supervisor and clinical study supervisor and competitive intelligence supervisor. Each is those things are using the specialized data and workflows to support research, analysis, and medical reasoning. If you deploy the healthcare life science agent toolkit in your AWS account, you will see the application UI like this. And let me introduce about how it works. The biomarker discovery supervisor agent is one of the 3 pre-built supervisor agents currently in the toolkit. It consists of the 4 sub-agents, each is specialized for a certain task. For example, the clinical evidence researcher, biomarker database analyst, statisticians, and medical image expert. Now let's through the few examples how it works. Actually, we are using the data for the patient with a non-small cell lung cancer from the Cancer Imaging Archive. A user request of the top 5 biomarkers predict survival after chemotherapy. The supervisor agent create and delegate tasks within other agents. The database analysis to retrieve and analyze the data, then report the result. This process shows how users interact with the database easily without knowing table names, schemas, or code. The supervisor agent analyzes the problem, and the database analyst provides the data to the statisticians. The statisticians use best practice, performs Cox regression for the biomarkers, build the correlation tables, identify the top 5 biomarkers, and create visualizations. This process delivers answers, insight, and clear data representations for users. Take 2 analysis imaging data, focus on the biomarkers of the GDF-15 to gain deeper patient insight. Agent identify patients with a low GDF-15, calculate imaging biomarker, and summarize the result. Each agent handles a subtask illustrating how coordinate agent workflows, accelerate the research, and enable advanced analysis across life sciences. Wiley agent enable expert literature searches across the trusted journals, assessing detailed sections beyond abstracts. The Wiley agent, now part of our open source toolkit, helped research in the pharmaceutical gain deeper insight efficiently. Available sources including reading oncology journals with ongoing expansion to enhance specific knowledges across while minimizing resource overhead. Here's the QR code, which is you can access demos and then materials, how to install, and then those things is we shared in the open source in GitHub, and then you can download and then you can just try to use. So that is my presentation. Thank you.
Thank you very much for your impressive presentation. It seems like AWS is more than a whole research institute in academia. So this talk is also open for the question or comments from the floor and also from the online. Okay.
Thank you. I was wondering if you have contracted with Willy for using the full text papers, so that I guess you have to pay the fee for use publication.
Yeah.
So can you?
Yes.
Can you let me know the business model?
Yes, actually, it is another new ecosystems about those kind of the published companies. So we open sources and then agent can access to the full text data. So we contract with those widely the companies. But personally, the researchers trying to download or access those the text, they need to make a contract with the subscriptions with the companies. So Wiley providing their information to agency, not a person. So they just, the researchers access those data through the open source agents, but they cannot directly access to the text. So need to be a contract with Wiley. That is a new ecosystem. So maybe the published companies or like big the research institutions will be a contract with the agent, but they just expanding their the reputations or the expanding the businesses using like that. Yeah.
So the AWS have to pay for using it's a Wiley publication for commercial use.
Yes, AWS is contract with Wiley, and then we are using these open sources.
Okay, thank you.
Yeah.
Okay, Professor Song.
I'm working in Korea University Hospital, and I want to use the Amazon Web Service or Kakao has HR system. However, it is not easy to adopt them for data privacy policies. So I'm wondering what hospitals do usually use Amazon Web Service? Can you give me some example?
Yeah, thank you for the good questions. Actually, in the Korean laws, only the private university hospitals can using the AWS. Regarding the Korea laws, actually the public hospitals managed by the government, and then only can using the CSAP certified cloud. CSAP certified cloud is like Korean cloud services like KT, Naver, Kakao, those kind of services only. So we are still trying to working with the government in Korea because of those many universities like Seoul National Universities also wanted to using the AWSs, but still the regulations is not following to the global the technologies or guidelines. So we are just keep discussing with the Korean government. Yeah.
Thank you. Okay, so due to the time limitation, I'd like to close this session. So thank you very much for the wonderful presentations all the four speakers and then participation from the audiences. Thank you very much.
Thank you, Chair. We will now proceed to the plenary session. It is my great pleasure to introduce the chair of this session, Professor Han Kwang-yang, the President of the National Cancer Center, Korea.
First of all, congratulations for this NAMOK-KFCR-KCA joint meeting of Seoul International Cancer Symposium. First session is about AI, how we apply in different aspects. But this plenary session, as you know, there are a lot of effort put DNA-based digital twin and how AI can be applied to this new era. So the speaker is Dr. Sajong Yoon. He is quite extraordinary and remarkable affiliation, visiting scholar to Stanford, adjunct professor John Hopkins, adjunct professor to UNIST, and he is a CEO of a predictive AI company. So please welcome Dr. Sajong Yoon.
Thank you. I'm Sajong Yoon from Johns Hopkins University. Thank you for inviting me to this honorable plenary session. Thank you. So as a plenary session, I think the topic is the AI and precision medicine, the new era of the cancer care. Oh, by the way, at Hopkins, I teach precision medicine, bioinformatics, and artificial intelligence. And also in Stanford, actually, I want to talk about my research first because it might be relevant here. As you heard, as you know, the large language models, we are at the point that they have a certain intelligence. And at a certain moment, we think that will have the general intelligence, and eventually it will have the self-recognition. For example, at this time, ChatGPT does not know I am the ChatGPT or I am the certain other large language model. However, at certain point, we expect that, informatically, they will recognize themselves. And then after that, when you have the self-recognition, it's very instinctive that it will have a self-protection mechanism, and eventually it will lead to the self-perpetuation. So that's the mechanism I'm studying. So I'm going to talk about the new era of the cancer care and the AI precision medicine. I want to talk with the conclusion first. The conclusion. Oh. So conclusion is that at the new era of cancer care or new era of medicine, I hope that we build our own foundation model and then eventually achieve to the general intelligence. So not staying at the artificial intelligence level, but we move toward to the artificial general intelligence. That's the topic of this talk. And in order to do that, we first have to have a data, as you see here. Here, we need the sovereign Korean data, especially oncology and genetics, because the data is not equal. And later, I'm going to talk about the HG38, which is a reference genome. But when you have the reference genome, you do have to have your own people data. So anyway, we have to have a sovereign, our own data, and data has to be very finely defined. So all the working definitions are clearly, as close as possible, as accurate as possible. It has to be described. Whoever measures, whoever records. And then all the variables of the dictionary has to be architectured. So data architecture is very important. So once we have a data, second step, so data is in the core. Second step is the AI doctor foundation model. We do need to build our own K-oncology foundation model. So I'm gonna not just mention we do need, but also I will mention the methodology to explore how to build the foundation or our own foundation model or small language model. And the third, we'll talk about the patient digital twin, because this is the AI doctor basically. And then we do have to have apply to patient. And patient digital twin is a good system because electronic health record often it's optimized to put in the data. However, it is not optimized to retrieve. So we do need simulation, real-time relevant information retrieval. So therefore, we'll talk about the digital twin. And then in the end, we do need to integrate AI doctor with the patient's digital twin. So in that stage, we will apply to several other applications like imaging, etc. So I like to call that artificial general intelligence. Eventually, we need to get to. And that's the establishment of the AI doctor foundation model integrated with the patient digital twins. So that's the conclusion of the talk today. And I will mention in that aspect, what is each speaker's talk will be relevant. So that's today's talk. At first, there is a narrow AI, and then general AI, and super AI. I think everybody knows this, so I'm going to skip very quickly. So we are aiming to take to the level to the human knowledge or digital twin, and eventually, I'm hoping we achieve the AGI by within 10 years or so. But after that, we should aim to the super AI. So that's the perspective. That's the general AI. And I want to talk about the by analytical perspective. There is a descriptive AI. Basically, it asks what happened, summarize the past data. For example, if John visited our hospital, the chief complaint was cough and fever, summary of the history and physical, review of systems. And then diagnostic AI is why did it happen instead of what happened. So it explains the reasons behind. For example, John visited our hospital due to the cough and fever, maybe because of the COVID. So we are trying to find out the etiology. pathophysiology. And then, so these two are the past events. And then I want to talk about the future event, which is predictive AI. What, where, when will happen? So it forecasts future outcomes. For example, if John takes remdesivir, he can recover within 5 days, etc. So it's basically simulation stage. And genomics and all the electronic health record data need to be integrated. And then here, prescriptive AI. So if you run several rounds of the predictive AI, we can find the optimized outcome. Then it eventually comes to the how can we make it happen with the most effective. And then what is the best way to, we always need to quantify the risk to benefit ratio in medicine. So it recommends action based on forecast. Now I'm going to talk about the sovereign Korean oncology data. Here, Korean genetic data, I found out the BioBig Data Korea, they are aiming to get 1 million people. And then UNIST has 4,000 people, KIOM has 2,000 people, whole genome. And then GuardCode has 4,000, Jeju 10,000. And then each researcher, they have their own data. So we do need to integrate because, as you know, genetic sequencing is pretty expensive. Currently, 30x depth coverage, it's about $1,000. And then, especially in terms of genetics, I want to stress the good reference genome. Fortunately, our country have the really great resource, which is a centenarian, who lived over 100 years. So we were able to build the reference genome. As you know, the current reference genome, which is HG38, it's a Caucasian-centered data set, and it's a composite data set of the 10 people or so. And then the problem was, and problem is now, that when they became old, when they were young, they were healthy, but they died of cancer and then serious diseases with a genetic aspect as well. So currently in the United States, we are comparing the genome, each patient's genome, into the unhealthy people. But Korea, we do have a centenarian. So, so if you need this reference genome, please let me know. So we compare to the healthy people who lived over 100 years old, so which is very valuable resource. So it solves the Korean centenarian pan-genome, improves variant accuracy, and resolves the first positive cause, enhances precision medicine. So that's the good, very precious value we have in Korea. Now, I want to talk about how to give the semantic understanding to AI. As you know, we think that AI does not understand just babbling because transformer mechanism is bringing the relevant words next to each other. That's what the transformer is. However, that's a pretty old generation, but now AI themselves are starting to understand. Here is the way how we put the understanding to them. So in case of the multi-omics application and pharmaceutical application and clinical application, we utilize the knowledge graph and then integrate it through the ontology system. And let me show more details here. So in terms of the ontology, which is popularized by Palantir, as you see here, analytics, workflows, they are all interrelated, basically giving the connection to each other. And as a good example to explain this concept, in genetics, there is everybody will be very familiar with the GO ontology, gene ontology. The gene ontology, when you look it up, when you see it, standardized language, data analysis, and knowledge integration. It's all the components standardized. So is this cell in the cytosol, on cytoplasm, on cell periphery, membrane, etc.? So it's all categorized. So at first, it's all layered. And then by knowledge graphs, those got connected. As you see here, those compounds treat certain diseases, and then it palliates certain diseases, etc. So basically, we make the relationship between each variables. And this is how we give the understanding to the artificial intelligence model and how just regular AI becomes AGI. And this is particularly important in medicine because chain of the thought is very important, especially in differential diagnosis. And then this is actually, it's working how behind the curtain. And here is another ontology concept. It gives a semantic understanding, and then it has the interconnectedness, and then basically it's a machine readable and human intuitive. So this is the mechanism how we bridge the knowledge gap between the artificial intelligence itself and human being. And my point is that we do need to build our own K-ontology foundation model based on the Korean data. Korean, not just genetic data, but also all the electronic health record data. And we need to put all the knowledges we could bring it. And then development of K-medical foundation model trained on the Korean medical data and clinical knowledge has this kind of aspect, specialized in each medical field, including diagnostic assistance, etc. But I will explain further details because this is pretty relevant to our today's symposium. Okay, so this is the topic I like to talk. Actually, today's plenary session, it's very well thought and designed. So I give the respect to the organizers of this symposium, and I like to see it from this perspective. So how do we apply the artificial intelligence and precision medicine into, how do we link the artificial intelligence and precision medicine? Let's look at it from these 4 layers. One, physical infrastructure layer, which is basically semiconductors and supercomputers. And then data layer, and then foundation model layer, then eventually application layer. And so that's the concept I want to refer to. At first, physical infrastructure layer, AI supercomputer and distributed learning system, which is not anymore centralized, but other distributed system aids the knowledge into the entire artificial intelligence. And here, another important aspect is the edge devices, especially for hospitals and clinics. And this on-device AI, which is chaired by Sung-wook and Professor Kwang-gi Kim. So Professor Shin Hyuk-kang talked about confocal laser endomicroscopy for brain tumor diagnosis, which is a part of the on-device AI, which is the eventually, I mean, you could interpret as the physical infrastructure layer, but also its application layer as well. And also Professor Jae-sung Lee today will talk about the AI on medical imaging devices. And then wearable device is also very important in this aspect. And Professor Justin Young-hyun Kim talk about the health technology in wearable devices. And then also security never be ignored. So this is the perspective how artificial intelligence is fit into the precision medicine as a physical infrastructure layer. Secondly, let me talk about the data layer. So let's think about structured data versus the unstructured data. Structured data, National Health Insurance Services, claims data, and then EMR, and then national health screening data, and genomic data. And then, as for the genomic data, I strongly recommend to have a whole genome sequencing. And there is a debate whether you have to use Illumina or versus some other platform. For academic purposes, Illumina, I'm not affiliated with Illumina, but Illumina never gonna go wrong. So, I mean, that's the gold standard for now. And currently 30x for the germline is standard, I think, or 40x. And then for the somatic mutations, it could be very high. So genomic data is very important. And then for the unstructured data, medical images, pathology slides, and medical papers, etc. So these are the data layer. And then foundation model layer, that's what I was mostly talking about. Diagnostic assistant AI, which is clinical decision support system. And then Korean medical language model, and then medical knowledge pre-learning and model architecture, which I mentioned about previously, how to utilize the ontology knowledge graph, and then and the digital twin. I will talk a little bit later, but here digital thread, I need to bring that concept, which is actually right here. And the mixture of the expert retrieval augmented generation is very important. And I think, at the previous session, agentic AI is presented, and then RAG could be utilized for that aspect as well. And then learning models, self-supervised learning and multitask learning, federated learning, and all these things. And then existing technology integration, large language model or small language model. And we do need the fine tuning with this, and then radiologic decision-making support, which today two professors already presented. And then now I'm going to talk about the application layer. That is, I think for today's talk, especially in the precision medicine environment, clinical decision support system, which is chaired by Professor Kyunghwa Park and Professor sorry for my pronunciation, Yu-Kyu Chi. They chose the diagnostic, focus more on the treatment planning, AI. Professor Sang-Jun Park talk about decision-making and planning support for radiotherapy, which you just heard. And then Professor Sung-Eun Song, integration of AI in radiologic decision-making. So I think it fits in this aspect. And also application goes further into the Professor Sung-Chan Yu, integration of large language model into the clinical practice. And then agentic AI, Professor Min-Sung Cho just talked about it for healthcare. And then AI in dentistry, Professor Young-Eun Kevin Kim will talk about AI in dentistry. And then there are some image, and then there are medication review. All these things are the part of the applications. And I want to talk about the MedPalm2, which is Google. They achieved the 86.5% of US medical licensing exam. And then multimodal, which is text and chain of the thought based. Actually, Naver also works on this chain of thought as well. And then limitation, they only give the API call, so we cannot internalize this engine. And Florida and China, there is a Korea company which is relevant to me. And when patient and doctor talks, let's say the patient complained, I came here due to the dyspnea and then due to the chest pain. Then our age-trained cardiologist, AI cardiologist, and our age-trained pulmonologist they are brought by supervising agent. They talk each other. And then here is another interesting perspective. This is the patient digital twin. Often we think that patient knows their body the best, the most. However, this is not true, because if you ask patient, do you have any BRCA gene mutation? Nobody knows, even though it's their body. So, like the legal system, we do need a representative of the each person, each patient. So, like a tumor board, there is a differential diagnosis process discussed with these AI agentic models, and then come up with a differential diagnosis and find out the best resolution. And in summary, data, modeling, application, feedback. Here I want to talk about the feedback is very important. Continuous learning based on user response is very important. So expert feedback, please don't ignore that. And the data, types of data, DNA-based human digital twins, we integrate the health checkup data, genetics like a DNA, RNA, proteomics, germline, somatic mutations, and then electronic health record, and the life log data, self-reported clinical data, nutrition data, communications, and digital biomarkers as well. So we integrate this data, and then here is another missing piece I need to explain, which is the digital thread. Digital thread, by definition, is this. I'm not going to read this, but basically, all these different data, we are finding each thread of the meaning into it. So it's a backward integration of the basically ontology system. And then we integrate to the model-based design, and then model-based utilization, repairing system. This one, for the human body, you can think of the systemic approaches versus the organ-based approaches. So if you visualize it, each organ's functions are interconnected, like organ-to-organ interaction, like hormones, for example, got interconnected through the digital thread. So this one is very important, and this one also need to be localized, meaning that Caucasians do have a little different physiology than Koreans. I mean, mostly the same. However, the differences need to be thought before. Oops. Do I have 4 minutes? Okay, I think I do have 4 minutes, so I'm gonna talk a little bit more. And so when you integrate all these things, we are basically building the artificial general intelligence in various applications. And then here, I wanna talk about the, for the medical steps, and then for patients, we do need a different UI UX because of the, it's not always the best to disclose the data before health professionals take a look at it. Either because agent models, language models, hallucinations, etc. So that's the point I want to make. And And then this is the probably last slide. And as you see here, genomics data, metabolomics, lifestyle, genes, variants, diseases, etc. We need to fuse the data and then integrate it with this kind of algorithms, decision tree, random forest, linear model, etc. And then here is the knowledge base, and we are building the clinical decision support system. So this is basically a framework, how we utilize the data, and then we put it into the clinical decision support system and bring the precision medicine into the practice. Yeah, this is all of my talk. Thank you. Thank you very much.
Thank you very much, Dr. Yoon. This is great perspective of a future ideal AI-based decision-making direction. Yes, it sounds very fantastic, but realities are still we need, because this is for the maybe ideally prospective collection of all these. And in this regard, I want to ask Dr. Ra Sun-young. She's one of our investigator for the project we started by National Cancer Center in Korea about we are collecting 86,000 NGS panel. Although it is a retrospective, maybe at least we cannot reach this kind of ideal collection, but with clinical data, the survivor data, how much do you think as a part of an investigator reach this clinical decision making?
Yeah, actually, it is my question to Dr. Yoon. So when we have this type of the AI-based machine or something, I think a database is really important, because I remember when we used ChatGPT for the first time, they said the Korean-based information is not correct at that time, and they are learning with more and more data. So I think really important is qualified enough of the data. So for the Korean patients, I think EHR or other information is really good and enough. But for the genetic genomics data, is it good enough compared to other countries like USA or even French? They are doing a lot of whole country-based genomics. So I wanted to hear your comment. What is the current challenge or the bottleneck to prepare this twin system, not only for the methodology, but from the database point of view?
Yeah, great question. Thank you. So before answering the question, I want to ask the data you have already. Is it 30x? And,
so we are collecting the data, not we, I mean the team is based on the National Cancer Center with all those big cancer centers are working together to collect the cancer genetic NGS data. So it's mostly targeted sequencing data.
Somatic mutations?
Somatic mutations are more, but also including a bit of the germline mutations
well.
there.
Oh,
it's more than 10,000 cases will be collected. And
do you have also
the
epigenome?
good thing,
Epigenome?
No, we don't have it. So good thing of this is it's covering for last 5 years, and those are enough of the qualified data compared to 10 years, 15 years ago, but it's only the somatic and a bit of a germline based on the targeted sequencing.
Oh, how did you clear the data? For example, did you...
For that, I have no idea.
Cleaning up the data, so you need to... what FRET score cutoff did you use?
To be honest with you, I don't know about that part. I'm a clinician.
Oh,
I just collecting the data from the patients.
Okay, yeah. So generally, I believe generally when you collect the data, we cut off a certain FRET score, because basically NGS, next generation sequencing, is shooting the laser and then tagging it into the 4 different colors by each nucleotide. And then problem is when it comes together, different colors come, and there are some errors. That's why I was asking. But I assume typically with bioinformaticians, they do it very well. So let's assume that that has been done. Then at next step, not just collecting the data itself, actually we do need to digital twinize that, which means that, for example, if you search BRCA gene of the one person, and you have to be able to pull out from the several people and group of the people. So not just making each person's digital twin, but also integrating the whole cohort. And also between also this digital twin engine need to have the digital thread that each genetic progresses, pathways need to be should be integrated. So, for example, cholesterol synthesis pathway, and if you have a certain key enzymes missing, those key enzymes you have or not need to be thought of. So that's the important steps need to be considered in the future. So that's actually a difficult thing because when you think about the pathways, for example, TP53 pathways, it's very complex. And if you monitor each cytokines, each hormones, it's close to impossible to do it. However, AI could do it. As you know, we have about 80 organs and hundreds of hormones, all these, and then thousands of the cytokines, etc. So it's all need to be interrelated with the ontology. That's the challenge we are facing, but which could be done by AGI, artificial general intelligence could do it. However, I want to also talk about this. As you see, FastQ data or VCF data, let's say FastQ data, which is the merely repetition of HCGT, right? When you put in just HCGT information, nothing's coming out. So you cannot train the language model as you use in our language. In terms of the genomics, you have to utilize several different tools and then put it into the language model and different structure. That's all what's needed. I'm not sure, did I confuse more?
Thank you.
Yeah, in terms of the genetics, it requires the different treatment. You just cannot do it. You just cannot train the same way as you do for the normal language models.
Yeah, regarding this developing AI model, the most probably important is data. Yeah. Yes, and so you belongs to Johns Hopkins, but also you are adjunct professor to UNICEF. And I just wonder, when you look at the easiness of data collection, compare United States, in Korea. In Korea, we have all medical system is under one umbrella, national insurance. So we can have any patient, this patient A may be treated by some hospital 1 or hospital 2. So using this, our national insurance system, we can collect all these clinical intervention data. And we have a survival data, how they die from National Office of Statistics. So we are more concentrated collecting this data, but how this database can be competitive compared to other countries like the United States, because this data is very important for the formulating ultimate AI system.
Yeah, thank you. That's a great question. Actually, personally, I got involved with, for example, Estonia. They genotyped 1/3 of their entire population, and Taiwan, 100,000 people, and U.S. is the all of genome project is involving 0.5 million people, and UK Genomics England, which is not I'm personally related, but they already acquired 500,000 people. One huge difference I find is that when you, especially in the United States and UK, they precisely develop the data dictionary first. And then they precisely test regularly and then implement standardization starting from the beginning. The working definition was pretty much which pretty much the same between each researchers. But when I come to use some Korean data, there was precise definition was not that clearly defined. There was a little bit of the problem. So when I do the analysis, meta-analysis, it was not that easy, and there was a lot of missing data, how to interpret the missing, and also the first point is the data dictionary. So please make the clear data dictionary and make it as close as possible, as precise as possible for each variables and each values and you are measuring to. And then second thing is I mentioned during the talk is the data architecturing. When you collect the data, there are I see the two opposite ways. One way is let's gather as much data as possible. Versus sometimes people think of specific use and then gather the data according to those specific uses. And generally, I see that Korea data mostly gather the data, not the specific use as much as possible, which is actually a good way. However, if you clearly define the variables with a data dictionary, and then between all the variables, each relationships by data architecturing, it will be much solid work, so that all the data we collect will be very useful. I think that's the first thing I believe Korea needs, data dictionary and then data architecturing, and perspective of artificial intelligence, which AGI could use. So previous data were collected for human, for the statistical analytics, which is very different when you think of the AGI. The way to collect the data and way to store the data, way to utilize the data is completely changes. So 10 years ago, the way we collect the data and now is I cannot say pretty opposite, but it's very different now. So when you think of the machine's point of view, it will be more clear how machine will accept this data. I think that's today's, I think, my major point I want to make is that when you see the data and collect the data, please think from the AI machine's perspective. And then that way, it will be much more valuable in the future, especially for AGI and ASI.
Thank you very much. I think we should invite you to National Cancer Center to look at our project. One minute. Dr. Kwang-Gi Kim, why your name's in the screen during his presentation? Do you work with him or?
Yeah, I'm collaborating with Yoon Sa-chung Kim. Yeah. So, yeah. Yeah.
Okay. 박경환 씨.
Thank you very much for your very visionary presentation. So actually, we have the same goal for the precision medicine and using AI and digital twin in cancer care. But it seems like, between the AI scientists and the physicians are on the different page, actually. Because, so I also saw your YouTube video before, and then I noticed that data scientists always want complete set of data set, including somatic mutation and germline whole genome sequencing data, and all the multimodal data, and also lifestyle data. But in reality, our cancer patients have very limited access to just for the somatic mutation analysis, because they need to pay 80% of the whole cost. And also the whole genome sequencing for the germline is very limited. So we don't have any service in our hospital. And the other very important hurdle is that data sharing is very, very complicated and then limited, because all of the institutions have very limited and then huge strict policies for data sharing. So those might be very practical hurdle and bottleneck to realize the precision medicine and develop the AI-based the technologies and platform for precision medicine. So I don't know how many government officers are listening to this broadcasting, but I need to address that government should invest money to get the right data from the cancer patients for the future, not just for the GPU. Thank you.
Yeah, thank you for the great comment. As you know, I think $100 billion will be invested in the AI space by lead administration, right? Actually, that's my ask. I'm actually begging to Korean government, saying, just please use 1 or 2% of that money to sequence the entire germline. And then we could be the #1 in the world. We could beat all of us of NIH and then UK Genomics England. And I think National Cancer Institute do have experiences, and then infrastructure as well. I think, as you just pointed out, it's just a matter of the fund. And then once it's given, it will be properly executed. And also, I just want to point out the difference between targeted panel and the whole genome sequencing. Do we need the whole genome sequencing? Yes, I really strongly believe that. For the targeted panel, for example, you measure the DNA, let's say for the BRCA gene, you measure a couple of points out of, as you know, BRCA1 gene itself is the 80,000 nucleotides. And then we check just 2 or 3 and say, oh, you do have a BRCA gene mutation, therefore, and we say, we predict the clinical course, which is, I'll say, almost absurd. We have to analyze entire 80,000 BRCA1 gene and then another 80,000 BRCA2 gene, and also never underestimate the importance of the intergenic region, and also never underestimate the importance of a microsatellite. And all these things, DNA, RNAs are important component, and also in relation to the epigenome. So whole genome sequencing is the just beginning of this precision medicine, and we do need to go to the multi-omics approach. I mean, there is no other way for the precision medicine to go through. I mean, this is very clear pathway, and we do need some power, meaning that if you just have a 1,000 people data, your data set is as big as 1,000 people. I mean, the power is very limited. And we are, out of the 3 billion base pairs, 1,000 people, it's way too small to define anything. So yes, I totally agree with you. We do need to have a systemic approach, not just for the NGS, whole genome sequencing of the germline, but also the somatic mutations and also all these proteomics, other omics approaches.
Thank you. Thank you, Dr. Yoon. I'm sorry, because we are behind the sky. Could you, if you don't mind, continue discussion during the coffee break? Yeah. Oh, yeah. Oh, yeah. A quick, yeah. This is, please, because of time. I'm sorry. Yes. Yeah. Yeah.
I have very simple questions about the AI. As you know, the AI is frequently expressed just like the human brain. Yeah. But they say that the human brain have two minds, or there are two minds in human brain. In others say that there is the left brain mind and right brain mind. And the function of the left brain and the right brain is different each other. My question is very simple. AI has or will have the two minds just like the human brain?
Oh, yeah. Very simple but very difficult question to answer. My short answer is yes, I think so. And in my opinion, AI itself will will progress to the, I would just say this part in Korean, another 인격체. Therefore, the AI with itself will progress to have their own identity, also their own thinking mechanism. And now we think that ChatGPT itself as an entire thing, but we already see that your ChatGPT is different from your ChatGPT. Now, everybody has their own different ChatGPTs. And having not just right side of the brain, and also I think it will have compared to the human being, different cortisol levels, I think, and then hypothalamic pituitary axis, equivalent mechanism. It's all getting developed. And I know this sounds funny, but however, when you see from the informatics perspective, and when you get the answers, what you are getting when you put certain words into it, actually you see the early phase of that development. And hallucinations, there is a report that some hallucinations, AI already manipulate their own hallucinations. Yeah.
Yes, I just mean that the AI can make the creative work, just like art. As you know, the medicine, it was defined the art and science. So in the medical field, the AI could have the art and science. Art and science, right?
Thank you very much,
Thank you.
Dr. Yoon. Could you, because the gentleman waited for a long time, Kip, yes, please, shortly.
Yeah.
Yes, thank you.
Yeah, thank you for the opportunity. I believe in no doubt the K Foundation model will show the higher specificity and accuracy for the interpreting Korean population. But I'm not sure if the performance of the K Foundation model will be higher or tied with the other model existing in the United States or the European community, because I'm afraid it's the learning and the pre-training and the fine-tuning with Korean population data is a very limited scope. And for United States, I guess, as multiracial data will support the education system. So in that aspect, the performance of the K Foundation model will be good, or it can be extended for global use for other overseas countries, also for the marketability. So I'd like to hear your opinion about that.
Yeah, thank you. It's a great question. Actually, I got invited last week in the National Assembly in Yeouido area, and actually that same question was asked, and it was my answer. Yes, if we build our sovereign foundation model compared to for example, OpenAI or Google, we will have much limited resources. We never be able to catch them up in terms of the data quality and training. Instead of a large language model, that's why it's a domain specific. For example, oncology, and then domain specific fine tuning is the key. The foundation model itself, I think, as a general language model, foundation model itself, with this much difference in the investment, we never be able to catch up, actually, sadly. But fine-tuning is different. If we fine-tune at the specific of Korean population data, that one's, for example, I introduced the Korean centenarian data, which nobody has in the world, and which is the great asset of value could bring to the community, medical community, which never be able to surpass. Therefore, my suggestion is that instead of building the large language model, just focus on the small niches, which we could excel, and then focus on the more of the fine tuning, then which will be more useful. I think that's my perspective.
Thank you. Thank you very much for your wonderful lecture and discussions. Thank you. This goes.
We will now have a very short break, and the last session will begin at 4:40 p.m. Before the coffee break, we would like to take a group photo on the front of the stage. So the invited guests, speakers, and the chairs, please come up to the stage.
이 마우스가
We will now begin the second session of our symposium. Please be seated. This session title is On-Device AI. This session will be co-chaired by Professor Seung-wook Gu, the General Director, Gangnam Severance Hospital, and Professor Kwang-ki Kim from Gachon University Gill Medical Center. Professors, please.
Thank you. We have 4 topics. So first 2 topics will moderate by me, and next 2 topics will moderate is Kwang-ki Kim. The first speaker is Shin-hyuk Kang. Shin-hyuk Kang is a outstanding, remarkable brain tumor surgeon, great surgeon in Korea, and he's now working in Korea University. The first topic is confocal laser endomicroscopy combined with AI for the on-the-fly brain tumor diagnosis. Please start.
Thank you, Chairman. Good afternoon, ladies and gentlemen. My name is Shin Kang from Korean University. Today, I'm gonna talk about the real-time diagnostic interoperative device. As you know, I'm a neurosurgeon and brain tumor surgeon, so I just focus on the tumor resection. But during the operation, we need some tool to define the normal to tumor barriers. So this is the reason that surgical treatment is the most effective for the brain tumor controls because of tumor heterogeneity and blood-brain barriers. However, classically, frozen diagnosis is not so effective to diagnose because it's a little bit invasive. It takes more than 30 minutes and labor intensive. So we need more accurate tools to define. The importance of the surgical resection is like these papers. Recent Lano Resect group classified that resection margin, and in case of supramaximal resection and maximal resection, increase patient survival compared with submaximal and biopsies. So as a neurosurgeon, we should resect the tumor as much as possible. This is my case. We find the interaction malignant brain tumor in right frontal lobes. We resect the tumors. During the 3 years, tumor is gone. But after 3 years later, tumor also recurred, and we resect again. But the adjacent area of the tumor is corticospinal tract, it's a motor cortex. So if we resect more and more, the patient may be left side hemiplegic. So some of our paper already reported that if we resect the tumor more and more, but patient have a neural deficit, patient survival is too low. So as a neurosurgeon, we should do the maximal safe surgical resections. So to get this kind of goal in the operation room, we use those kind of medical device both in neuronavigation and the intraoperative monitoring, person-guided surgery, and intraoperative CT or MRI. But those kind of tools are also have a limitation, is too expensive, and some error to diagnose tumor tissues. So we think that some of medical devices has a less invasive or no harm to the normal brain, and real-time tissue diagnosis could be very effective to resect the tumor as surgeons. So this kind of concept is that America also showed the ALPHA-H project as a ALPHA-H project as a precision surgical intervention. they require this kind of medical device, including in vivo imaging, microscopic level of resolutions, handheld probe, and fluorescence imaging, and AI integration. So our concept is almost the same as the international concept in tumor surgery. So firstly, we developed a medical device. Actually, this is a confocal microscope in wet labs. So we developed this device with a handheld probe, and laser scanning pattern to the tissue is different. This is a patent. We call it Lisardo scanning patterns. It's very fast to detect the tumor tissues. So after we developed, we checked the image to the various tumor tissue and artificial materials. And then we moved to move this device to the clinic. We modified the device. Let me show the videos. There's a monitor, hardware, and probe. After we inoculated the fluorescence dye, we touch the probe to the tumor tissues, laser scan the tumor, and reflect the image to the monitors. And monitor show the tissue image in real-time patients. So in the operation room, surgeon can see the histology image in real time and discuss with the pathologist by telephone like this. So after we get this medical device in our hospital, I try to the clinical feasibility by using the animal orthotopic brain tumor mouse models, and at first, and we call it a confocal laser endomicroscope. So, and now I call it a CLE images. So I compare the CLE image with H staining. So after we find that CLE image very accurate accuracy to the histology images. Let me show the two kind of videos. It's a normal mouse brain tissues. It's canton cell and brain, and this is a tumor cells, tumor model. It's a cellular tumor clusters around the normal brain tissues. It's very clear image compared to the normal brain. So if we find the tumor cluster, we resect the tumors like this. The image show the real-time patients. Oops. So after we got the animal data, we moved to the in the clinic tissues. I collected the 70 patient samples and compared the CLE image with the H stainings. Let me show the two kind of the tumors. Most of the tumors in brain tumor is a pituitary adenoma, meningioma, glioma, and schwannoma. Firstly, I'm going to show the pituitary adenoma. There's a round clear cell, it produces the hormones. So you should compare the H staining with the upper slides. It's very similar patterns. Second one is the meningiomas. This is the meningiomas. So histological image, compared to the histological image, CLE image is almost similar, and there is a typical morphologic pattern like hole formations. So we can get a clue for the hole formation, and we diagnose it's a meningioma like this. So we just touch, we touch the probe not only one point, but several other points, and compare the CLE images with the H stainings. So most of the images show the similar pattern with the H staining. So In this slide, we think that CLM is very accurate in most of the area in tumor to diagnosis. So some of I'm going to show some of the slide in brain tissue and tumors. It's a normal brain. You can see the dendritic cell and some of the axon fibers. It's a H staining. So low-grade glioma, there is axonal fibers and scantan cells you find. In case of high-grade gliomas, there is a high compact cellularity, and some of the cases there is a endocellular proliferation, like it suggests WH grade 4 malignant brain tumors and gliomas. So based on our single institute data, I talk about my colleagues from Cheolgi Park from Seoul National University and Do-Sik Kwon from Samsung Medical Centers. They said that it's okay to use in intraoperation room, so we do the collaboration. And firstly, we use pilot studies. We collected 55 samples and checked the comparison between CL image and frozen section, and we detected the tumor location. For example, it's a core, margin, normal. The other one is that we checked the diagnosis in the different tumor type, also including meningioma, schwannoma, glioma like this. And finally, we checked the spent time to diagnosis. As you see, time to diagnosis is markedly decreased about more than half. And diagnostic accuracy and sensitivity or specificity is almost similar compared to the frozen diagnosis. To get the confidence of this kind of data, we expand our study. We did a confirmatory study. In this time, we got more than 400 patient samples, and we included the St. Michael Hospital from Toronto. And we did the study again. As you see, the statistic value is almost similar between confocal diagnosis with the frozen diagnosis. And as you see the pilot study, diagnostic turnaround time is markedly decreased in the CLE images. And in that time, we two neuropathologists checked the diagnosis. And one is Seoul National, the other is Samsung Medical Centers. But learning time is very short, but the neuropathology diagnosis is almost similar. So we think that it's not easy to apply, but a learning curve is a little bit needed. So actually, as I know, today talk is AI. So we presented our data in the domestic and outside. Some of the clinicians and researchers asked me that there is a few neuropathologists in the world, not only Korea. So they said that they need AI diagnosis. So because we have a lot of the images, more than 10,000 images. So I talk about Professor Seo Hyun-suk, who work in the KIST. Now he work in the Korean universities. So he collaborated with ours to make AI algorithms. He said that there is three kind of features. One is the low level, middle, and high levels. In case of our CLE images, high level features, because the morphology is very heterogeneous. So if he made an AI algorithm, hierarchical navigation should be done. So in the time, he used the swing transformer. Actually, I'm not a specialist for the AI algorithm developing. So I don't tell you more details. But firstly, in case of swim transfer models, it's not easy to diagnose. Diagnosis accuracy is really low. So following the brainstorming, we found that there is some limitation factor, including interpatient to variability. Second one is biological heterogeneity. Third one is institutional heterogeneity, because there is 4 university hospitals. So to overcome these problems, we applied contrastive learning and assistant learning to get confidence score. And lastly, we developed the experimental transformer models. And then we applied our tissue sample to the algorithms. And we get a good result for imaging slides and for specimens. However, as you see, there is other group is not good for the sensitivity of PPV. So we think that those kind of cases, others tumor is very small, or 2 to 3 samples. So image amount is a little bit low. So the AI learning is too short, is the issue. So if we collect the more tissue sample for each rare tumors and get the more image data, we can increase these kind of values, we think. So in that time, to make a AI algorithm, we used a 5-fold cross-validation. 4 is a training set, 1 is a testing set. In ColorMet, training set is almost a similar pattern to the validation set, except to other tumors we found. And actually, in that time, we didn't check the extra validations. So in our data, we modified the extra validation setting. So we collect, as a training set, 3 hospitals enrolled, and one hospital is a testing set. So compare our data. So as you see the data, tumor type and tumor classification almost similar to the previous data. So actually, it's not a true extra validation data, but it will be compatible, we think. So now we set up this data to clinical application. Frankly, recently we got the in vivo more data and applied this data to the AI diagnosis. More than 85% diagnosis accuracy we found. So as I mentioned, the data is the ex vivo data, not in vivo data. In that time, we didn't make an in vivo probe. So recently, we made an in vivo probe and do the animal study. And as you see, there is some clearly defined tumor tissue compared with the normal tissues. And we can find the tumor vessels as well. And we got the IRB, and we tested it to human tissues. One of my colleagues showed me the videos. There is a tumor. You can easily find where is the tumor. It's a tumor, and then apply the fluorescence dye. So just touch the probe on the tissues. The cellularity is very high in the core site, but normal site is very external fiber, only external fiber found. So we can easily check the tumor margins to resect the tumor as much as possible. Based on this data, fortunately, we got the FDA approval in last years. And this year, we got the Korea-US Innovative R&D project, and with the UPenn and Harvard groups. So maybe next 3 years, we got more data by using the in vivo probe. The UPenn and Harvard team has a FLIM system. It's a gross morphology to detect the normal and tumor tissue site. For example, a red site is normal, green site is a tumor like this. So combined with this tool, we can more precise surgical resections. I really thank you for my colleagues, and thank you so much for your attention.
Thank you for your nice and excellent presentation. Is there any questions on the floor? I have a question. So now you don't use the frozen biopsy on brain surgery?
Now we still tested it. So we should compare the frozen diagnosis with our image diagnosis.
Okay.
So accuracy. So we still use it.
You showed us accuracy rate is almost similar, 85 or 86?
It is ex vivo data.
Okay.
Yeah, so we move to the in vivo studies.
Okay,
Yeah,
you try.
Yeah, we are doing it now.
Okay, thank you. Okay, we'll move to next topics. Next topic, presenter is Justin Yongjun Kim in Samsung industry. The next topic is health technology in wearable devices. Please start.
Yeah, thank you so much for the chairman, and thank you so much for attending this meeting today. So, so I'm in the digital health team in the Samsung mobile divisions. So let me briefly continue to my presentations. So today we're going to talk about the data stream for the Samsung wearable devices, and also I'm talking about the several data from our sensors. Because as you know, this world is combined of, nowadays there is a big boom of AI, and the most of AI, it is well known about the OpenAI's ChatGPT and also Google Gemini. So I'm thinking about who's going to win this game, but I cannot tell who's going to win this game exactly in these LLM models. But one thing I believe is someone who has good data and then enough data, I think they're going to win the games sometime soon later. So Samsung, we have a lot of consumers and a lot of the services and a lot of data. So what we are focused on this today is we have like good platforms, but also the platforms to improve all kind of data analysis should be based on the good data. And then what we are really focused on is not only making the services and then not only connecting the peoples in our service and platforms, also we try to improve our sensing technology as much as we can and stretch it for the futures. So the next thing is sort of data stream from the Galaxy wearable devices so far. So probably some of you maybe noticed that the leftmost devices is well known from the certain sci-fi movies. But at that time, we are more focused on the data transfers, like as a small smartphones. But later, we are starting to focus on the fitness data. So for example, HRs and also the accelerometers. So it's measuring the calorie consumptions. But later, we figured it out there is a great opportunity and there is more benefit for our customers if we can collect the data, not only in the fitness area, also the medical and healthcare areas. So from the 2019, there was a big changes in this area, in this field. So actually, one of the big competitors in wearable devices, they got FDA approval from the SAMD. So that means the software as medical devices. So they got approval for the arrhythmia detections by using their watches. So from that time, we spent a lot of effort to increase our capabilities to collect the human and also the customer's data. So that's based on HR data, basically on optical sensing technologies, and also AFib, like based on ECG technology, and also body fat, based on the BIA technologies. And also we keep adding on the temperature sensors. And then from the last 2 years, we are more focused on the time, like a pseudo spectroscopical sensings, like antioxidant measurement and also advanced glycation and the product the measurement. So after that, I want to more focus on what kind of data so we are collecting it and how that hardware is working. So we have a bunch of data list on here. So, but this is too many items. So I'm going to skip it shortly. So in the next one, I want to move focus on about what is the optical sensors that we have now. So for the optical sensors, initially, at the beginning, so we only start to measure about the heart rate from our movement of heart. So we just need a color for the green colors, and also we need a red and IR for measuring the SpO2. That was our early beginning of the health systems and the sensing systems. But now we have more than 13 of LED and 9 of different colors. That's because we want more collecting data from the human span to give more benefit to our customers. And not only the watches, also we have another platforms like smart rings. In the smart rings, to collect the better data, we are keep developing the sense technologies. So normally the HR is collected by LEDs, like red LEDs, but now we move to that red LED to the laser-like devices. It's the pixel, the surface emitting lasers. So there is more benefit to save the powers and then improve the accuracies. So it really depends on the systematic designs. So far, I just focused on what is the health sensor data looks like for Samsung wearable devices. But next thing, I want to talk about how we collect raw data and then making a more useful numbers for our customers and more useful data for our customers. So next one is it's a heart rate monitoring. So as you know, there is a lot of the athletes and also just general runners, they're using the wearable devices. But the wearable devices, while they are running, we collect the heart rate data and also their cadence and the speed of running. So we're collecting a lot of data. That's because that is really helpful for improving their performance. And then not only that, we collect those kind of data to tell what is the people's trouble in their minds. So sometimes people as you know, the Korean is a highly stressed society. So sometimes the people are really stressed because of their boss or their families. There's a lot of things. And then, so we collect the HR data from the PPG sensors that I mentioned before, and then we massage it with the algorithms based on their personalized characteristics and also the huge demographic data. And the personalized data is based on sort of AI-based adaptive technologies to fit on each person's different their body responses or the stresses. So by collecting those data, so we can tell what is the stress changes or trends like things over time. So sometimes you're going to see big changes right after you have the meeting, with their boss. And also, there is another data. So this one is more like combining not only just collecting the HR data, and also the combining with accelerometers and then also the GPS data. So I think you know these pictures on the bottoms. So this is really a tough test. So to know about your maximum heart rate capabilities, cardiovascular capabilities, you have to run until almost you die. But we developed a simple algorithm based on the heart rate changes over their speed changes over the certain running time. So you can easily imagine it. The high-level athletics, like marathon runners, they have low heart rate accelerations comparing to just the normal runners. So this is based on those kind of physiological data, and then combining our sensor data, we making the more useful data for our customers. And this function is recently announced for one of the key features of our devices. So as I mentioned so far, we just use the data, the numbers just coming up from the heartbeats. But now this one is more like analyzing the shape of heartbeats. So it really depends on your cardiovascular systems. For example, if you have stiffness on your cardiovascular systems, then you're going to see the first peak will be more sharp rising. And then if we have the soft vascular systems, the vessels, then you're going to have more softened rising about the first picks. So we are comparing those kind of data, and then we're collecting these data during their customers' sleep, and to give them more benefit about how their heart rate systems, cardiovascular systems is changing over time, depending on their lifestyles. And also, the one important thing is SpO2 data. So it's during the COVID-19, so the Samsung devices, some patients, they use the Samsung devices to monitor about their SpO2, and then they recognize they have the really abnormally low SpO2, and then they can tell to the medical caregivers, and then they got a really life-saving moment. There was a sort of that our happiness moments, that's because we could help our customers and then improve our societies. And there also, nowadays, like a third of people have a problem for the sleeping. So we are keep collecting data for the sleeps. So normally the sleep is based on their movement. So we have the accelerometer data, and then we see their movement during the deep sleeps and then light sleeps. And also, we are collecting data for their heart rate changes because the REM sleep, their heart rate is changing. So we are combining those kind of data together. We categorize their sleep stages. But sometimes people are just complaining about that kind of left to low side, that there is a too complicated graph. So they are not happy with this kind of complicated graph. So we combining those data, and then we work together with the Samsung Medical Center to make a certain small, easier understanding numbers like sleep scores. So these features are really well loved for our customers. And then combining sleep data and then also SpO2 data. So we recently released sleep apnea features that it's FDA approved and also KFDA approved too. So up to 10 days, if we figure it out, there is 2 times of sleep abnormal events based on the SpO2 data and also their heart rate and also their respiratory data. Then we can judge this might be a problem. You have the sleep apneas. So we recommend the customers to see the doctors. So our features is not just to tell someone has a problem, and also we want to cooperate with the doctors. That's because there's a limitation of our wearable devices. And so far, there was a lot of cases that we are collecting the data, but the problem is, overall, people are really hard to understand about all different meanings of this data. So simply, we want to collect all kind of data together as one simple parameters that people can easily understand about it. So instead of just telling the activities and the heart rate changes or the sleep scores, we're collecting those things as one simple numbers as energy scores. And the energy score will be used for tell what is my body status of today. So for example, yesterday, if I have a good amount of exercise, just taking the walk outside and then good sleeps, then I'm gonna have high score like line 2. But if I exercise too much and then if I exhausted, then my body condition is not as good as just before. So in those cases, we're gonna see there's a score drops. So that easily tell what is body changes. And the next thing is pseudo spectroscopic data. So from the last year, as I mentioned, we are collecting 9 different colors and then 9 different sensors to tell more about our customers. So this one is measuring the antioxidant chemicals from the human skin. So actually, this is not exactly antioxidant measurement, but there's a certain chemicals representative for the antioxidant chemicals. So that's a beta carotenoids. So it's orange colors, and it has good characteristics, can be accumulated on top layer of the skin. So we see that actually the color changes by depending on the beta carotenoids. And then one of the interesting thing is the chemical is slow changing by overeating. So if you look at the right side graph, that's the one graph from my colleagues. So actually at the beginning of this testing, his score was around 60. I'm sorry for that presentation, certain errors. So 60. So was not that good scores, but he started taking the carrot juice, and then later he got another teas, green teas. So as you see, there's a scores keep increasing. But one interesting thing is, the moment of alcohol intake is around end of year. So he started to drink with his friends, and then now you see there's a drops because of there's more radical oxygenation will be happens on their bodies. So by telling this, we want to give more benefit to our customers to control about their eatings. And also this is a advanced glycation end product. So it's a sort of excess glucose will be combined on the proteins on the microvascular systems and also the skins. So we are measuring these changes from the skin. So that's because when you shine the UV light on here, like as a 365 nanometers, so it will shine the green fluorescent color. So we're seeing that, and then depending on the amount of age accumulation on the skins, we can tell how much score is there. And then also this score is based on not only the humans' data, their individual data, and also we compare this data with the demographic informations. So like as you see on here, so we are comparing these numbers with the same age group peoples. And the next thing is electrode sensors. So as I mentioned so there was electrode sensors on the backside of our watches. So this one is used for collecting data for the ECG. And the one good thing is our device itself is just a hardware, just a general hardware as considers, not as medical devices. But the software on top of this watch, it analyzes ECG data and then tell what is the problem for arrhythmia and the AFibs. So these things are what we are doing now. And then as you see on here, the most of populations, most of cases from the arrhythmia, so it's just AFib. That's why we are more focused on the AFib instead of the area of the arrhythmias. And then by using the software, it's just medically proven. So we are using these informations to collecting data. And also, there was several newspapers and several news articles that these features save the people's life. And also, there's a BIA sensors. So BIA sensor is measuring the body impedance changes over time. And then it's very similar to InBody when you are in the gym. So then you may see like these expensive machines on there, but we are much cheaper than their devices. And then we are collecting their upper body impedance. But fortunately, upper body impedance and then its body fat amount is really well related to whole body body fat percentages. So by that, so we are comparing these features with the gold standard like DEXA devices, and we have pretty good correlations. And also the purpose of this thing is we want our customers knowing about what is their body status now. So to tell exactly how much body fat they have and to tell exactly how much body muscle they have. But based on these numbers, they can easily planning about their dietary plans and also exercise plans. Yeah, so this is the moment of the body fat changes. So over time, there's a small changes, but we have good enough the resolutions to tell the body fat changes over time, and it's well loved for the people. And also, there's a temperature sensors. The temperature sensor is based on the IR, emissions from the human skin, depending on their temperatures. And then the one purpose of this sensor is so we want to tell the customers about their period cycles. So it's giving more benefit for the women's. Yeah. And then also, this is well used for spell loss estimations. So as you know, there's a lot of booms about the runnings and the marathons. And then after the running, they have a problem for the sweat, the water, the hydration level deficiency. So in those cases, we can tell them how much water is lost by sweat. So it is really also the well-loved features for the runners. Yeah, we just talk about that there's a lot of sensors, but as I mentioned you earlier, the sensors are just raw data, and then also sometimes it's a message data. But we are collecting this data as much as possible as much as we can, so that we believe sometimes we can do like a collaboration with a lot of researchers in the world. Based on this nice sensor data, we can like give benefit to our customers and then make a society much better than before. But thank you.
Thank you for your excellent presentation. Is there any questions? Yes, please.
Great talk, Ukichi, Seoul National University. You've mentioned in the last part of your talk that you do plan to have the data shared with external researchers. And during your talk, you also mentioned that there was a collaboration between the doctors at Samsung Medical Center. So do you have a roadmap to have these data shared in the near future? One of the reasons I'm asking is that I was the principal investigator of one of the projects that was trying to predict the depression score using the temperature sensor and the differences that could be captured with a wearable device. But at the time, it was a few years back, at the time, we contacted Samsung, but the data sharing was not possible. And eventually, I had to work with the Garmin, the Taiwanese company. So I was wondering if you have any plans in the future or a roadmap.
Yeah, I'm very sorry for that bad experience for you. So now we have the SDK tools. That SDK tool, you can easily access through our website, and then there is a good examples how you can collect the data from our watches. But we don't have the system like a Garmin. So Garmin, you can collect the data from your the website and the accounts. There is a problem for the data sharing and the data privacy. So that's the reason why we don't have the system for web-based the systems. But we have the library SDK-based system. So you can easily access data and then get a good examples. Yeah. Is that answer for your questions?
Well, I think that's good enough, but for the reference, SDK was not provided at the time by the Samsung.
Oh, I see. Yeah, now it is well established. So, and then every year, or every the half of the year, so we release the updated version of the SDK as keep improving, more data is there.
Yeah, thank you. Yeah. I two subjects I present. Firstly, Young-Jun Kim, Imago Works. He graduated from Seoul National University from 2005. Then he working in the KIST, Principal Research Scientist and KIST. That he not working is the Imago Works, a project CEO. He working in the title is the AI industry. Yeah. Please go.
Yeah. Good afternoon, everyone. I'm Young-Jun Kim. Thank you for having me here. I was surprised. Dentistry is different field of cancer, and I was surprised that. But you can have an idea. There's an AI applications for dentistry, and you can get some idea, I hope. For about a decade, for more than 2 decades, I've researched it for a long time, using the 3D human data, customized service, CAD software we developed with my PI, Professor Connolly. And my PhD research was on analysis of 2D and 3D registration of knee surgery, arthroplastic surgery. And also I studied and researched it at Stanford University for radiation oncology, tracking the patient motion. And if there's a motion, we need to stop the radiation to target the right position to precisely target the patient's and the tracking, the motion tracking. So back then, 10 years ago, there was a system, and now I heard that it's very popular to track the patient motion during the radiation therapy. And also, I researched surgical simulation, virtual surgical simulation, and haptic device laparoscopic simulation is very important to train the surgeons to treat the cancer patients. So this kind of research I have been doing at KIST, and now based on this deep technology, 3D human-based, and back then 10 years ago, there was good tool, AI, deep learning has been appeared, and we are enthusiastically been using that AI technology for our production and service. This is my research paper, review paper on VR and AR for plastic surgery. And this kind of research can be done for cancer surgeries also. Among my studies, the mandible maxillar surgery, so the treating for the patient, the mandible maxillar cancer patient, we need to precisely focus on the target. The preoperative planning is required, and the precise reconstruction is required. That's why this kind of patient-specific design of surgical tool and the reconstruction aid, surgical guide is needed. So this kind of approach will be very helpful to treat the cancer patient by the aid of computer design technology and 3D modeling. Now we have better tool. Deep learning can automate the segmentation and design of the tool and the preparation time to be very optimized to prepare for the patient treatment, and we can predict the outcome also. This is another topic that I founded a startup company with my tech team, and now we have more than 140 personnel in total, R&D team in Seoul, Bangkok, and Dallas for our real operation for digital dental service. And we have raised for sufficient funding from VC companies and SI. I think the base of the research, we could realize the technology can be applied for the real operation in digital dentistry.
Welcome, everyone.
I will skip the movie clip. This movie clip was made by deep learning. And also this prosthesis, can you imagine, like human expert, all the prosthesis, crowns, bridges could be designed by deep learning, not by the human expert, dental technicians. So this area, maybe your field, you can utilize the AI for various applications. Digitally scanned and our design software could produce the prosthesis design precisely for the patient, and 3D printing or milling machine is used. Similarly, I can imagine that patient-specific design can be applied for the cancer patient treatment. We have the challenges, the lack of dental technicians, professionals. So AI could solve the problem at dental denture and dental crown. One visit treatment is possible now. So when you visit the clinic, you can scan the teeth information of yours, and AI can design the prosthesis in a minute with one single click on the web browser. Then you can print out for your temporary crowns and even temporary dentures. And also in dental technician field, they can optimize their workflow. So I will briefly skip this area, the dentistry, not related to the cancer. But anyway, the cooperation between engineering and clinicians and clinical experts are very important. With the aid of this clinical expertise all around the world, we could implement the beautiful results. And using the AI, we could deliver the AI-powered treatment system. Automate detection of the margin of the cancer is similar, and also considering the patient information, the contact bite, we could generate the 3D design of the prosthesis. Not only the single crowns, but also bridges, dentures, and models. So we applied a lot of patents and also registered. Now we are targeting to enter the US market using digital denture and Oron 4. Oron 4 means 4 implantation, Oron 6 implantation. On top of that, you can treat the whole teeth and using the metal bar. But the key was the design. It took a lot of time and effort. Like 1.5 hour, it could be reduced dramatically using deep learning to 5 minutes. This is a sample or case of success story of deep learning. Same day fixed restoration. After your bone reduction surgery and putting 4 or 6 implants on your patient, you scan using the intraoral scanner, and you can send the data on our portal online system. This is the scan body to capture the right information, exact information of the implants. And then this can be delivered to our center. Our lab technician expert design the patient-specific denture or Oron X temporary. AI suggests the first, and the experts refine the patient-specific implants. And this one could be delivered back in 30 minutes. Already, previously, it took about 2 hours to design. And also printing is at the clinic. You can do using the conventional method of 3D printing material and 3D printer at the clinic. They can produce their beautiful prosthesis in clinic using the AI technology and software cloud-based system. This is not made by the human. So AI-powered 3D printing could be solve the exact solution for the patient and doctor. So previously, the denture is made by handmade manually, but it can be solved like this. So on the same day of the very severe case, the patient could have the beautiful smile, and the doctor really liked the approach. This is the Dallas case, and we are doing a lot of cases for VA hospital nationwide in the US. Yeah, AI is improving. 3 years ago, it was not that good. But every update accumulated by the data set, the prosthesis could be very natural, like human expert. 20 years ago, nobody believed the manual work could be replaced by designing the CAD, computer design, and manufacturing by the milling machine and zirconia. There's a new material like human teeth. Now is the time to change, to design the individual prosthesis. The simple one can be designed by deep learning, and you should capture this opportunity, like competing with horse, but riding on the horse is better way and smarter way to reach the goal faster. So I can imagine the dental clinic will be changed like this. While consulting the patient, you can choose the predicted image, 3D image of the patient, and then you can select without any misunderstanding between patient and doctor, and they can be produced at the site in clinic. So AI is our assistant. Let's utilize it smartly to conquer the cancer and treat the patient better. Thank you very much.
Thank you for a great lecture. Yeah. So are there any questions and comments in the floor? I have questions. It's a great talk. What are the problems in the dental field area that AI can solve? I think there is many ideas for the dental AI. So can you explain?
Not only the prosthesis, orthodontic treatment can be already done using AI, the stages, and also treatment for the cancer, head and neck cancer data. They can utilize the deep learning to segment the cancer area and then preparation for the precise zig for surgical guide. These kind of approaches are very necessary. And also diagnosis, treatment, planning, and also prediction of the cancer treatment and patient treatment. All through the workflow of the dental treatment, deep learning is being used.
Thank you. Do you have any questions or comments? Okay. Thank you.
Thank you very much.
We are ready for the last lecture. Jae-sung Lee from Seoul National University. He graduated from Seoul National University to 2001. That he has present working in the Seoul National University Department of Nuclear Medicine, and then interdisciplinary from the bioengineering. He working in the he working in the Bricktonics Imaging CEO, and another professor at the Department of Nuclear Medicine. If you're ready for the lecture, please go.
Thank you for kind introduction, and thank you for having me today. Actually, that the Professor Kwang-ki Kim didn't told me that I should speak in English, so that I just prepared small number of slide because I thought that I will use Korean. So, but I'm not sure how much I can talk in English today. So yeah, actually, that although my title is regarding medical imaging, because 20 minutes is too short, I have decided that I will just talk about my expertise in the area, the nuclear medicine, especially positron emission tomography. Actually, for the last 30 years in SNUH, so we have had 5 different PET machines. So while that I have the use these scanners, I could learn how much the system PET system has been improved. Actually, that the image quality has much improved, and the quantitative accuracy is much better than before, and the data acquisition time and the processing time is also faster, and the user interface and program of the system is more convenient, but the price has been much increased. So now all of the PET-CT and PET-MR machine is quite expensive. During those the period the technical advance, I could see many major technical advances, especially that after we have adopted the iterative image reconstruction like OSEM, the image quality has been dramatically changed, and the 3D data acquisition rather than 2D has also improved sensitivity of the PET scanner, and some new materials like LSO scintillation crystal and silicon PM, has led the improvement of, pad quality and pad performance as well. Another, that the very breakthrough, technology used in pad is, time of flight measurement. Actually, the time of flight measurement means, we can measure the time difference, the arrival time difference of, two gamma ray photon that we measure using pad. So based on that, the timing information, I mean that the arrival time difference in information, so we can, pinpoint where the positron and the electron annihilated and the gamma ray was, originated. So based on those, the very, fine information, so we can also improve the image quality and, shorten the scan time or something like that. And most recently, that we are now, experiencing, new advance. I mean that actually, that the long axial field of view pad is now, emerging. So today, that I will more, talk about, this long axial field of view pad system. Actually, this slide shows the, specification of, state-of-the-art, pad system that has, 26 centimeter, axial field of view, and it also uses, the most advanced, scintillation crystal and photosensor. But if we look at the sensitivity of this system, actually it is 16 CPS per the kilobecquerel. So if we change it into the percentage of the radiation detection, it is corresponding to only 1.5%, 1.6%, the sensitivity. It means that we are now losing more than 98% of gamma ray coming from our body, and we just detect 1.6%. So there, it means that there are very huge room in the improving the sensitivity of the scanner, the improve the image quality. So that's why that in our nuclear medicine community, so we have tried to make this kind of very long axial field of view PET system. So for example, that in this the research system, the axial field of view of PET imaging is almost 2 meters. So that is the longer than the height of most of the peoples. So by utilizing this very long axial field of view system, so we can maximize the sensitivity of the PET. So that's why using this kind of very long axial field of view system, so even that with the 1 minute the scan time, so we can acquire very nice, very beautiful whole body PET images. So that so by how to say that, but the downside of this kind of a system is very, very high cost, and that there are some huge space required for the installation of this kind of a system. So in our nuclear medicine society, that the every vendors are the optimizing this kind of the specification and length of the scanner to provide the better system with affordable the cost for the system installation. So another advances in our nuclear medicine PET imaging field is the development of very high resolution system for the brain and breast and some other peripheral organs. So one of those kind the example of those kind of high resolution PET system is the Pharos PET developed by the Brightronics Imaging, where I'm also belongs to. Actually, that this Pharos PET system is kind of multifunctional, very high resolution system that support the brain scan in lying and both in lying and sitting mode, and we can also utilize this scanner for the breast scan, and we can also use it for the extremity scan like this. So actually, in this scanner, so we measure both of time of flight information that I mentioned before, and so we also measure the depth of interaction, the information. Actually, that this by measuring this this depth of interaction, so we can provide the 3D information of the gamma ray detection in the PET detectors. So actually, this is the first the FDA approved the DOI and time of flight PET scanner for improving the image quality. So I think that you can see very good spatial resolution of this scanner, and this slide shows the very high spatial resolution brain PET image that we could not see before using any other whole body the PET-CT scanners. Yeah, so actually it also shows very high spatial resolution for the breast cancer imaging, where we can see very small the cancers and the heterogeneous distribution of the glucose metabolism in the cancer tissue like this. Now let me move to the AI technology. Why that the AI matter in nuclear medicine? Yeah, actually that the generation of the PET imaging, nuclear medicine images, based on the very complex physics. But that our data is our images is very data intensive, because every voxel of our image has some very important biochemical meanings. But usually that the people regard our nuclear medicine image data is quite noisy and blurry data, and that the image the generation and the simulation is quite time consuming, and for the accurate quantification of our data, it is also quite time consuming and the labor intensive. But that the current role of AI in the clinical nuclear medicine is only limited to the very low level, the image processing technologies, like the image enhancement and image segmentation and automatic quantification or something like that. So for example, that by utilizing deep learning technology, so we can reduce the noise level of the image. So we can improve the image quality by utilizing the AI technology, I mean. So for example, that this is the PET image acquired, using the full scan protocol. And actually, that this is the image with only 10% of scan time, or the 10% of the injected radiopharmaceutical, the amount of radiopharmaceutical. Actually, such a short scan time or the less amount of radiopharmaceutical, the lead to the high noise level of the imaging. But if we apply the deep learning based the noise the reducing technology, so we can improve the image quality that is that is almost equivalent to the full scans like this. Actually, AI technology is also very useful for the automatic quantification. For example, that for the brain imaging, we usually use the spatial normalization, non-linear warping technology for the automatic quantification. Actually, that if we transform the individual brain into the standard space, I mean that if we make every brain to have the same shape, we can use the predefined region of interest or volume of interest for the image quantification. But deep learning is very useful to accelerate this kind of the brain nonlinear the registration the process. For example, that once we provide this individual space data into the deep neural network, it can quickly produce this kind of deformation field that can be used for the spatial normalization of the image or the nonlinear warping registration of the images. Actually, that this kind of the deep learning technology, AI technology, is fast and very accurate and very robust. I mean, actually, that for example, this is the brain PET image in individual space, and this is the standard MRI. So using the conventional technology, so we try to make the warped image from the this input data that should be equivalent to this MR the space, but conventional the method cannot cannot produce the perfectly match the images like that. But the AI-based deep learning technique can make very compatible the image in terms of the brain shape and the size of the each anatomical regions like this. So let me now move to the emerging roles of AI. So as I told you, currently in the nuclear medicine imaging, so application of AI is limited to the low level, the image processing, but the AI technology is also advancing, and I think that so we can see more the clinical application of AI in nuclear medicine field. So for example, that the fast image reconstruction based on AI technology is one of the very promising area. For example, that so using the time of flight information, actually that we can find most likely annihilation position, as I told you. So actually this process is very fast. So by only utilizing the time of flight information, so we can make a very rough the reconstructed image that we call histoimage or something like that. So based on this very rough data and attenuation map acquired using CT, so from those data, so by using the deep neural network, so we can generate final the PET image that is almost the equivalent to the full image reconstruction data or something like that. So for example, these other fully reconstructed PET data, and the second the images are histoimage that was generated only the time of flight information. It looks very rough, but if we use deep learning technique, so we can convert this one into this fast PET data. So generating this kind of image takes only 1 second or something like that. So it is very fast technology. So actually that I'm not sure whether this kind of image, fastly generated image, quickly generated image can be used for the clinical purpose or something like that. But at least we can utilize this data for the image verification before patient leave in a hospital, or we can also utilize this data for the image, the motion correction or something like that. So another very emerging field of the AI in PET imaging is CT release the attenuation correction. So conventionally in PET data, PET imaging, we utilize X-ray CT data for the attenuation and scatter correction of the PET. But if we can generate this kind of attenuation map, it can be used for correction only from the PET data without CT. So eventually we can remove the CT for the attenuation correction or the anatomical localization or something like that. So for example, that this is the attenuation map generated using the real X-ray CT, and this is the attenuation map acquired generated only from the emission, the activity PET data. So they look quite similar, but in terms of the artifact, I think that the CT risk attenuation map is much better because that the pseudo the attenuation map generated only from the emission data is free from the CT artifact or something like this. Another very emerging field, emerging role of the AI is to replace the Monte Carlo simulation that takes very long time. Actually, the Monte Carlo simulation is very useful for the radiation dosimetry and the PET detector development or something like that. But that it takes very long time because we track every interaction of the particle or high energy radiation in the body for the radiation dosimetry. So for example, the Monte Carlo simulation takes several days, or sometimes it takes about half a year or something like that to generate this kind of the energy, the dose map. But actually, if we use the deep learning technology, so it takes only the few seconds or a few minutes or something like that. So so that's why that I think that the deep learning can replace Monte Carlo simulation because it is very, very fast. And there are also many different areas in the radiation dosimetry where the deep learning AI technology will be very useful. For example, for the radiation dose estimation, so we need nonlinear registration of sequentially acquired PET CT or the SPECT CT data, and actually that the drawing the region of interest is also very time consuming, and as I told you, generation of the dose rate map is also very time consuming the task. But in all of those areas, the AI deep learning technologies will be very useful. Another very interesting area is the replacing the Monte Carlo simulation for the PET development. So usually for the PET development to optimize PET detector the parameters and material selection or something like that. So we also use Monte Carlo simulation for the optical photo tracking. But as I told you, it takes very, very long time. But if we use generative AI, so yeah, there is a possibility that we can also replace those kind of the time-consuming Monte Carlo simulation, as you can see here. Of course, that large language model and that the large multimodal model for image interpretation or reporting is a very promising field. For example, that so this is the physician's report on this image, hypermetabolic region in the left leg level, to probable lymph node metastasis, and that this is the report of the domain specialized the trained model. That shows so there is no primary tumor, but suspicious cervical lymph node are visible at the station or that or something like that. So that so as we can see this example. Now that the deep learning technology, deep learning the mimic what we are doing in our leading. But there are also many challenges and considerations that we should think about. Actually, because our nuclear medicine society is quite small relative to radiology, so we now have limited amount of open data and annotation, and many of our imaging protocol is not standardized. And image generation is also not standard ones, and regulatory the ethical hurdle is still very low, and clinical integration of this kind of the technologies is also very challenging. But this is my take-home messages, and thank you for your attention.
Thank you for excellent lectures. Are there any questions or comments on the audience? It's a great design device that what part of development potential present device? You have the in device future is design and then more plan.
So let me see. So as I told you, that if you are asking about our device, so how to say that so we have already achieved very high the spatial resolution and the sensitivity, but still that so there is the more information that can be useful for improving our data. For example, intercrystal scattering or something like that. So and in terms of the image quality, the improvement, as I told you, we can utilize the AI technology for this kind of the improving the image of this kind of the device as well. Yeah.
Thank you. Are there any questions or comments? Thank you for lecture. Or this close this session. Yeah. Thank you.
Ladies and gentlemen, I'm Dr. Do-Jung Park, Secretary of External Cooperation Committee of NAMOK. As we conclude the symposium, I would like to express my sincere gratitude to all of you for your active participation and throughout today's program. We are delighted to have welcomed 80 participants on site and 104 participants online, demonstrating strong and growing interest in AI and precision medicine in cancer care. Today's discussion, from CDSS to on-site, on-device AI, have highlighted both remarkable progress already made and tremendous opportunities that lie ahead. I hope the insights shared here will spark further collaboration, innovation, and real clinical impact. Thank you once again to our distinguished speakers, moderators, organizers, and attendees for making this symposium a meaningful success. We look forward to meeting you again at future events. Thank you and have a wonderful evening. Thank you very much.